Ready to learn how to write GDScript and release your first Godot game? Let's do this. There are a lot of other Learn Godot courses out there, but most of them shy away from getting you too involved with the code. Uh, that ends now. Maybe you're new and you've downloaded Godot and thought, hey, this is supposed to be easy. Why do I have to write code? What are these horrible little symbols? Who am I? How did I get here? Why am I covered in blood? Who is this strange man and why does he say I owe him money? By the end, you will understand GDScript, Godot, and how they work together in a general sense. Have a game ready for release as a web or PC build on a storefront like itch.io, or at least a way to share it with your friends. You'll have a surface understanding of a few common programming patterns. You'll have enough understanding to modify the code we work on together to make something unique. And finally, you'll be able to go on and explore these topics in greater depth and become a better programmer. We're going to do this in GDScript. GDScript is the default language for Godot, and it's heavily based on Python, which is one of the most popular programming languages in the world. This is a high-level overview of code-first Godot. I want to take you up to the dizzying heights of programming so you can look down and see the lay of the land below you. We're going to have to gloss over some details to get you thinking about how code works together to make a game. There's going to be challenges throughout too that will actually get you making those connections yourself. I think code first is a better approach to learn Godot, since in code you can trace the game logic more or less completely, and there's less unknowable dark magic like physics interactions. This is also more or less how I work on the data-driven games that I'm interested in, like turn-based strategy or RPGs or puzzle games, whatever. These can be made pretty easily in code alone. The final project for this video is an implementation of the classic Snake game. It's fun, it's extensible, and we can build it without getting into UI or enemy AI or like physics. Our version of Snake, or at least the version that I'm going to end up making here, is going to be a bit over 100 lines of code. 100 lines that you will understand. Whereas modern large games are made up of millions of lines of code, the basic building blocks are exactly the same, but the complexity level is much higher. You have to start somewhere though. Don't use AI to do the thinking for you. Please try to learn and get comfortable with difficult things before reaching for that. So start by following my lead. When you feel a bit more comfortable, pause, try some different things. What can you change? What breaks things? You might freeze your Godot, but you're not going to accidentally nuke your computer. And just be chill about this. This stuff is dense. You're not going to get it right away, maybe. Take breaks, review, ask questions in the comments, help out other people in the comments when they have questions, and look up stuff in the Godot documentation. I'll put a link. It's very well written. Let's get started. The first thing you need to do is download Godot if you haven't already. It basically works out of the box and it's pretty small, but if you need to get it, it's a free download at godotengine.org. I'll be working off the 4.7 version, so I recommend getting that. The basic code that we write should function with any of the Godot 4.x versions, though there might be some UI differences that might be confusing. Still, if you have weird bugs, the first thing to do is make sure you're on the same version as I am, Godot 4.7. So when you open up the Godot executable, you get something like this. You can create a new project, which is what we're going to do. Don't worry about any of the settings here. We're just going to give it a name. I'll call it Learn GDScript today. I'm going to click on Create. This should take us to the Godot engine. Let's have a look here. All right, so the Godot engine is split into a few different panes. If this is all overwhelming to you, that's totally okay. The big one in the middle is our game world view. You'll see it defaults to 3D usually, but we can click on the top here to see 2D. If we're working on a 2D game, this is what we want to work in. If you're working in a 3D game, you'd swap between the 3D view and the 2D view for a UI. Great. Otherwise, we have a few other panes here. On our left, we have our scene view. If we click on, say, Create 2D Scene, it will add a scene to this, and this becomes a tree with everything that's in our game world. Below that is usually the file system. Again, this may vary for your layout. Mine looks like this. The file system has a file system under it. You'll see a folder called res. We can create a new folder under that by right-clicking on it and call it, I don't know, sample scenes. And in here we can create a new scene. So we'll go to create scene. We click on 2D scene and we'll call this scene GDScript basics. You'll see that we're now in the GDScript basics scene here. We can exit this other one and click on don't save. And now we have something called GDScript basics at the top of this scene tree. When you click on something in the scene tree, you'll see in the inspector on the right side, you'll get some options here. We'll cover these a little bit later, but mostly we'll be working in code. At the very bottom, you have a bunch of tabs also, output, debugger, and then some other ones. We will be looking at output and debugger during this. So let's just leave it on output for now. So let's add a script to our Godot. So it's very easy to add a custom script in GDScript. We will select a node in our scene tree. Right now we only have one. It's called GDScript Basics. And we press this attach script button, and then it will try to put it in the same place as our scene lives with the same name, but .gd, and that's perfectly fine. Don't worry about this. All of the defaults here are just fine. Okay, this takes us to another view here. This is the script view. So you can go 2D, 3D, script. And you'll see that we are on the GDScript basics script. I'm going to zoom in here so that you can see more clearly as I type. Great. The only thing that shows up in our script is, well, this thing that says extends node 2D. Now we're going to cover this in more detail, probably not in this series, but eventually. But what this generally means is that there's a type of thing called a node 2D, which has some properties. I can tell you that some of the properties are like having a position in space, for instance, and also being able to be in a scene tree. And our script has all of those properties plus everything else we want to do with it. So that's fine. And then we can just type things here. The first thing I'm going to type is a comment. A comment starts with a octothorpe or a, what's this called? Hashtag, whatever. And then anything else you type on the line after the comment will not be dealt with by Godot. So this is a comment and it will be ignored. You can put as many of these as you want and it doesn't matter. Nothing will happen at all. But we're not writing code so that nothing happens. We're writing code so something happens. And the next thing I'm going to do is create a little function that's going to run whenever this scene loads in. So that is called ready. And to get it to work, we do func ready, func space underscore ready, and then parentheses. We'll do a little arrow, which is a hyphen and a right angle bracket. And then we're going to say void and then a colon. And then I'm going to type pass after this with an indentation just so that it doesn't give me an error right now. So what I've done here is declared a function called ready underscore ready and said that it doesn't return anything. We'll cover that later. It doesn't take any values or arguments into it, and it doesn't do anything. Now, ready is a special function in Godot. A ready function, which is always underscore ready, will always be called as soon as this node enters the scene or the scene starts with this node in it. So what can we do with this? We are running this, I promise, but it doesn't do anything and we can't see it. So the first thing we want to do is figure out a way that this does something. So I'm going to show you a function called print. So for print, we want to make sure we are indented one in by pressing tab. That means that whatever we do here is within the ready function. We type the word print, and then we put parentheses, open and close parentheses. And then inside the parentheses, we can put any text we want. We can say, hello, I am ready. I'm going to press Control S or Apple S to save this. And then we now have functionality in our game. So to run our game, you can see up in the top right a run project option and also F5 on your keyboard will do it for you too. So I'm going to press F5. It will give you a prompt here saying no main scene has been defined. So we can click on select current and that will select our current GDScript basics scene and run it for us. You'll see it'll open a window that's got the game world, which is empty in it, but also in the output on the bottom, you may have to select the output tab. You will see it say, hello, I am ready. All right, so I have a first challenge for you. That is print something that tells us your name. You can use a fake name for this too if you want. So I'm going to ask you to pause here and think a little bit and then try to do this using the pattern I've shown you above. If you are overwhelmed and confused, that's cool. Just keep going. So pause. Okay, great. Let's try this out then. So we look up here, we see, okay, so the pattern seems to be we have print And then we have quotation marks around some text. And let's try that. So I'll do print, hello, my name is Hovering Skull. Okay, now let's play it to see. Hello, I am ready. Hello, my name is Hovering Skull. Terrific. Okay, that's great. Ready always runs at the beginning for one of our objects or our scene. What about if we want to run something over and over and over again? So we have another really common function here that we can do for that, and that's called process. So similarly, we do func and make sure this is not indented because this is a new function. Do func underscore process, and then it's going to give you some information here in Godot probably. It's supposed to be delta colon float and then arrow void. So we've seen arrow void before, and I haven't told you very much about it, so don't worry about it. It means it doesn't do anything, or it doesn't return anything. But this new delta float might be of concern to us. And that just means that whenever a process is called, it gets in a number that we're going to call delta, which is a float, and a float just means it's a decimal number. And process is called by Godot engine, just like ready, but it's called every single frame. You might have heard of games that run at 60 frames per second. Process will be called that much. If your game runs at 60 frames per second, it'll be called 60 times every second. Now, let's just see that in action. How can we do that? Let's just do another print statement. We'll say print, and we'll say processing. Let's play, and you'll see, holy, okay, so your output gets filled up, and it's running at, I'm going to say, about 60 frames per second. And you can look up to the top of your output window here, and you'll see you have your two print statements from ready, and then you have processing, and that runs a whole bunch of times. Awesome. So print doesn't always take in a string literal, which is this. It can also print anything, any data from our system. So we could also try to print this delta value we get. And so let's see what that looks like. Do print delta. And this is going to blow up our output window, but that's okay. So I'm going to do play, and I'll stop it. And you'll see we get processing, and we get a lot of the number 0.16667, mostly. But occasionally it's a different number. And what does this number represent? This number represents the number of seconds since we called process last. And you'll see that it is almost always 0.6667, 0.016667, but sometimes it's not. And that's because sometimes frames take a little longer or a little less time for various reasons. This is important though, because often we want to make sure things, for instance, move at a smooth speed and not at the speed of your processor. Don't worry about that too much right now. You might be asking, why is it always 0.01666, etc.? And I think that's because that's probably 1 divided by 60. And we can test that out by printing 1 divided by 60. And you'll see, oh, yeah, you'll see it comes to 0 because we're doing integer division, which we'll cover later. But we need to do float division, so we have to give it that value. And so you see 1 divided by 60 always comes to 0.0166. Okay, cool. I'm going to use comments to comment these two things out. And that way, even though process is still going to run, it's going to ignore these lines. And this is a handy thing to do sometimes. Let's talk about how code flows. I'm going to run again. You'll see we have hello, I am ready. Hello, my name is Hovering Skull. And you'll notice that those match up with the order here. It will always be in this order. You're never going to run it and see this come out in a different order. So for your next challenge, I want you to add another print statement that's going to show up between those two statements. Okay, and that should be pretty easy. All you have to do is print another statement. Save and press play. Hello, I am ready. Another statement. And hello, my name is Hovering Skull. So you're already reading code and understanding the flow here. The flow is it will go from top to bottom, usually. And we can always check the flow by using the debug function. So debug is another really useful tool that a lot of new programmers don't know about. You can access debug mode by mousing over to the left-hand side here, and a little red button here is going to show up. And if you click on that and you press play, you'll see that once we set a debugger here, it stops the execution here. You'll see this yellow arrow, and then you can use this step over, or F10, to move between each thing. And eventually it's going to hit our process, and you'll see down here in the bottom, it gives us the value for our current delta. You can stop the program, and you can remove the debugger to make the program run as usual. So that's how control flow works usually. it does get a little more complicated, and I'm going to show you a few things for that. So one of them is functions. So we already have two functions here represented by func, ready, and process, but we can create our own too. Let's say func do a cool thing. It's got the same syntax as above. I'm not going to underscore it for reasons that aren't important right now. And then you just want to put a little hyphen arrow, and you can give it a return type. Void is fine if you're not going to return anything from it. We'll talk about that later. So the thing about functions is we can do things inside of them. We'll do another print here, and we're going to print I'm in a function. And if we take this function name, do a cool thing, and if we put the parentheses after it like this, maybe guess what's going to happen. What order are our statements going to come out in? So we can play to see if our intuition is correct. And it looks like it goes, hello, I'm ready, another statement. And then when it does this, it goes into here, plays this one, comes back, and then it prints this last thing. And we can even test that in the debugger. So F10 to go down. You're going to have to click on step into F11, but that will take you to this. And then if you go over again, you end up back here. So functions take you out of the current flow and run through whatever the function's flow is. But within the function, that flow is going to be top to bottom. It gets more complicated though. Now, one thing that you might want to try, and it will cause problems, is what if you call a function within itself? So what do you think is going to happen here? Once you have that intuition, play it, and what you'll see is that we get something called a stack overflow. And that's because this calls itself so many times that Godot says, whoa, you don't have the resources for this. I think you're doing something stupid. So be careful about that. This is called recursion. There's safe ways to do it, but we're not going to cover that here. So don't try this at home. Or do, it doesn't matter. You'll just get this error. Okay, so control flow, it gets a little more interesting when we talk about loops. So we'll do func do a loop. So what's a loop? A loop is when we do the same thing more or less over and over again over some sort of data. Don't worry about that abstract description too much, but basically we can do what's called iterate, or go over a list of things or a range of numbers and do something within that loop. Let me show you what that looks like. We're going to do for index int, and we're just doing the same thing here where we add a type to this, and an int is an integer, so like 1 2 3 4 5 0 whatever, in range, and we'll do 0 to, we put a colon after it just like in functions, and then inside of here we have to indent again, so we're in 2 indents, and anything 2 indents in here is going to be inside of our loop, and then we can just print index. Okay, a couple new things to think about here. One is that we have this weird syntax here, which I'm going to try to break down for you. First of all, range 0 4, it just makes a list of numbers from 0 to 4 non-inclusive. So we'll make a list of numbers that are 0, 1, 2, and 3. Now 4 and in here takes each of these and turns them into this index variable. We'll talk more about variables later. And then it prints that value. Now, what do you think happens then when we call do a loop? So I'm going to play this and we can see if the output looks like we're expecting. Yeah, so 0, 1, 2, 3. It just prints each of those numbers for us. And I'm not going to go through the debug here, but you can. The debug is going to show us going here 4 times, and it will show you the value of index. That seems kind of useful. What if we don't want to print every number? What if we only want to print, I don't know, even numbers? We can do that by using a conditional statement. And this is another way we can modify the control flow. We can do a conditional like this, if, and then we'll say, for now, I'm just going to write if true, we can print index. This is a conditional. A conditional, it says if something is true, do something. And true here is doing nothing. It is just saying always do this thing. We also could do if false, and this is called a Boolean. A Boolean is a type that is only ever true or false. But we can do something more interesting here too. Let's just try. If we have if false here and we run this, nothing gets printed from the loop. And if we have if true here and run this, everything gets printed from the loop. But what if we say if, well, we have a few options here. We could just say, we could just look for specific numbers. We could look for any specific number here. We could say if index equals 0. Note that I'm using two equals here. In many programming languages, because we use a single equals to assign variables, which we're going to handle in the next section, two equals means is this equal to that? And this becomes true if index is 0, and then we run this. So what do you think is going to happen if we run this? Yeah, it only prints the 0. Great. So what I want you to do next is a new challenge. Only print the 2. Should be pretty easy. You try that out for me, and we'll move on. Great. So to only print the 2, all we have to do is change this to 2. We just check if index is 2, and we print that one. So we can do that. 2. Wonderful. All right. So we can also do something a little bit more interesting here. And I'm going to show you something that we'll come back to, but we can check if something is even by doing this. We'll cover this in the upcoming math section, so don't worry about this syntax too much. But we can say if index %2, this is modulo 2, it means we take the remainder of index divided by 2 equals 0, print index. This is a quick way to check if something is even. We'll talk more about this. Modulo, don't worry about it too much now. We run it, we get 0 and 2, which is correct. Okay, so you can see how control flows now from the top to the bottom. Whenever you see a function, it goes into that function. Whenever you see a function, it goes into it. And whenever there's a loop, it goes over this as many times as are in whatever the range is or whatever it's looping over. And whenever there's a if, we can go into here conditionally if this if condition is true. One other quick thing is we also have else here. We can do a similar thing. Again, we need to colon. We can say print not even, and then we'll play. There you go. 0, not even, 2, not even. Else runs if is false. A few other quick things to cover here. One, I want to emphasize indentation matters. We indent by doing a single tab, and then if something is within a function, it goes a tab in. If something's within a loop, it goes another in. If it's within a condition, also in. These are called like blocks. Vertical spacing, like enters, don't matter. They don't do anything. This line is meaningless. It doesn't matter at all. Spelling usually matters. This has to match the name that we give our function here, or else it will fail. Spelling within strings and within comments doesn't really matter that much. It won't change your program very much. When you write processor ready, they have to have this underscore before them, or else Godot doesn't know to run them at the beginning or every frame. Often, if you mess one of these things up, you will get an error. So if I call it do a cool thin, you'll see function do a cool thin not found in base self. That's kind of a warning for you to make sure you spelled it right or you're in the right place. You also see some warnings here. You'll see line 19, unused parameter. It's just warning you that we're not actually using delta anymore. And if you want it to shut up, you can just put an underscore there. The variables that show up as arguments like this, you are allowed to change the name as long as it matches the name within the function. Okay, that's the basics of how code flows here. We're going to work on variables and functions next. Okay, next let's talk about variables, functions, and constants, and also types. So to do this, let's make a new sample scene. We'll go down to the bottom left here. We'll right click on sample scenes, the folder. We'll click on create new scene, and we'll call it variables and functions. Great, that should show up in here. You're going to want to double click on that. And you'll see at the top here that we're in that scene. I'm going to exit GDScript basics. Great, you'll see on the left side in the scene tree, we have variables and functions up here. That's correct. And we'll also want to right click on it and click on set as main scene. This means that when we press play, it's going to run this scene rather than the GDScript basics scene. Don't forget to do this or else you'll get confused. Okay, and then you'll notice here in the code window, we're still looking at GDScript basics.gd. Let's make a new script. Remember, click on variables and functions in your scene tree. Press this button. We'll call it variables and functions.gd. That's fine. Create. Okay, cool. Now we're looking at our new script. And just to make sure that it's running, Well, what can we do? Let's just make a ready function. You remember how to do this. Func ready void colon indent, and all you want to do is print something. So we're doing variables. And press F5 to play the game. We're doing variables. So it looks like we have that set up. Let's talk about variables. A variable is something that lives on a class up here or inside of a function in here that can store some sort of value that we can use later or reassign. You could maybe think of it like a box that you can put something in, or you can take something out, or you can replace something inside. So a variable looks like this. We will type var, we'll type the name of the variable. This is up to you. You just have to make sure you can reuse this exact name again later in this script. We'll call it my variable. And then you can give it a type. This is technically optional, but I recommend always doing this. I'll give it the type int. We've seen this before. This is an integer type, which is like a normal counting number without a decimal place. And then this is a completely legitimate variable now. It lives now on this class, and we can look at what's inside of it. So we'll do print, we'll print my variable, and this will give us the current value of it. And we haven't set a value for it, but you'll see that it will give us something. It'll give us an integer, and maybe think about what might be the default here. What might we choose as a default number for an integer if we don't choose something? So let's play it. And it gives us a 0, which makes some sense. That's just the nothing of integers. Wonderful. Now we have another option here. We can use a single equal sign, and we can give it a value. So we could give it a value like 50, and then when we play, the print will give you 55. Now, if you try to give it a value that is not an integer, like hot dogs, the string hot dogs, you're going to get this issue here. It'll say error. It'll give you a line number 3, and it says it can't assign a string to an int. And this is good. This is telling you, hey, you told me this is an int, and you're giving me the string hot dogs. Like, what's going on, man? Now, if you don't do that, you can assign this anything you want, and you can reassign it. I think that's kind of dangerous. Usually you want it to be a single type. Now, another thing you can do with integers is reassign them. So we can do my variable equals 62. And then if you print my variable, we'll see, and we know how code flows now because we did the last section. We'll print what? Well, we'll print the current number of my variable here. We'll change it to 62, and then we'll print 62. And let's run that. 55, 62. Now let's talk a bit more about types. So we've seen some types already. Int is a type. Void is kind of a type. We have some other options here. So we have other numerical types like float. So float variable, going to be a float, and a float looks like that. It's a number with a decimal place. We'll talk about why you need both of those in the math section. You can also include a Boolean type. That's just called a bool, and it is true or false, and no other value is allowed. String types also work. A string is a piece of text. Remember, you have to capitalize this type for reasons I'm not going to explain right now. And all of these work how you would expect now. So why don't you try to print off some of these? And I'm not going to make this a challenge because it's really easy. You can print my string variable. Hello. Wonderful. The type system goes way beyond this. Every single piece of data that you manage in Godot is going to have a type. That includes stuff like the sprites that we render on screen. It's going to include even our custom class types here. We can create a brand new type of something just by adding class name, variables, and functions up here. And then it's totally legal to say something like this. And yeah, and if we don't assign something to these more complicated types, you'll see that they come out as null by default. So let's try that. Print my variables variable and play. They'll just say null. And null is a special type that means there's nothing in this box, man. So certain types will have a default type. String will give you an empty string that looks like that. My Boolean variable, a Boolean will give you a false by default. Floats will give you 0.0. Integers will give you 0. But complicated types are going to give you null, which says, hey man, I'm empty. One quick other thing to look at here is how reassignment happens using debug. So if we debug here and we play, remember we reassign to 62 here. If we play, we can see in the debugger window, we have my variable 55. In fact, you have all of your variables here. And then as we go through the program with step over here, F10, 55, 55, and then after this line is executed, my variable is now 62. So this is a really important thing to do if your variables seem to be having the wrong values. Then one other quick thing about variables is to show you something that looks like a variable but is absolutely not variable, and that's a constant. So constant uses a different keyword, const, but otherwise this is exactly the same. So we'll call it my constant number. We'll make it 66. We'll give it a type to. And what we're going to do with this is, well, or we can refer to it in the same way. So my constant number is going to be, what, 66, right? I'm going to remove the debugger. So in output, we see 66. But if you try to do this, you're going to get an error here before you can even run your program saying you're not allowed to reassign the value of a constant. Why would you want this? Well, a lot of coding is about restricting what people can do so that it's more clear what is happening and you can chase down bugs more easily. And it's useful to have some things that you can never change. And often usually type constants with screaming snake case here. So it might look something like this in a lot of code, but it doesn't actually matter. That's just convention. And you might use this for lots of things, like if you declare, I don't know, the gravity in a physics simulation, you might want to declare that to be 9.8, or if you want to declare the number of tiles on a chessboard, the length and width of a chessboard, those are always going to be 8, so you can just put 8 there, that kind of thing. Just put the number in, you have kind of a label for it where it's clear that this is the width of your chessboard, that kind of thing. Let's talk about functions again. So we did make a custom function in the last one, but I'll show you some more things about that. So remember, we can make a function by using the func keyword, naming our function, giving it parentheses, and then a arrow into some type. You now know this is a type, or in the case of void, a lack thereof. So do a thing is a function here that we can call here. And why do we want functions? So the cool thing about functions is they let us reuse bits of code. They also let us name bits of code. So even if we only use this once, it's important because it sets this chunk of code apart and says, hey, this is the part where we do this thing. Functions need to have a body. That's anything that's indented underneath it. If we give it the keyword pass, it just says, don't do anything here. We could also give it return, and that will pretty much do the same thing. When you return on a void function, it just leaves and goes back to wherever it was called before. Functions can also call other functions. Remember, before we called this function itself, but we can make another function like do another thing. And it's totally okay for us to do that here. This will run here, go into here, go into here, we'll return back, we'll return back to this part of the code. It doesn't matter what order we declare our functions in a Godot file. So if we put this up here, it will work exactly the same as if we put it down here, because all of these are properties of this variables and functions class, and variables and functions knows about all of them before we even run ready here. However, within one of these functions, it does matter what order you put things in because they are executed sequentially. Typically though, when we are building our files here, we like to put our variables at the top. In fact, constants usually go above variables, and then we put our functions after. And there are some more ordering rules that we will not really cover here, but generally the thing to do is variables first, functions second. Let's talk about types and functions. So right now we have all of our functions returning void. This just means that whatever happens in this function just happens and nothing comes back from it. But if we give the function a return type, say int, now when this function runs, it will return an integer into whatever variable we have. So if I do var my function return integer int equals do a thing, when we run do a thing, it should return an integer for us. So we can do here, return 5. So what happens here is when we get to this line, we run do a thing, we go into do a thing, we do another thing, and then we return the number 5, and then this variable will have the number 5 inside of it. We use var here, we're declaring a brand new integer, a new box, but we could also put it in our old box, which is also very useful. We can make my variable equal do a thing. Totally okay. Now this is changed on the class itself rather than inside of the function. So any other function outside of this is going to have this change happen to it. This is a little confusing, so if it's burning out your brain, don't worry about it too much. But when we declare variables inside of functions, they only last for the duration of this function and can only be accessed within this function call, pretty much. But if we declare variables on the outside in a class like this, non-indented, these variables are accessible anywhere in any function inside of this, as well as from the outside using something called dot notation, which we'll look at a bit later. We can kind of think of some of our functions as little factories. So we can make a function called func add two numbers, and this is a little cool little preview for math. We'll make it return an integer, and we'll make it take in two integers. So we'll call them a int and b int. So we now have declared that this function needs to be called with two integer variables, or arguments as we call them when they come into a function. And then inside of it, after one indentation, we can do return a plus b. What's this going to do? Well, it takes in these two, it adds them, and then it returns them as this value. So let's do, call it var my sum equals int equals add two numbers. And we can add literals like 5 and 8, but we could also add a variable, so we can just do my variable. Both of these are types of integers because we know my variable is an integer. So if we print my sum, have a quick think and guess what this is going to return for us. I'm going to press F5 to play it, and we'll see. 13. So why is it 13? Well, because my variable at this point is 5. Then we add that 5 to an 8 in here. It gets returned to my sum, and then we print that number. So often functions function as little factories that can take in some sort of ingredients and output some sort of product. Often you're going to want to return early from a function. So you could have a function that is going to divide things, and it can check if something is 0 and then return some default otherwise. So we'll say divide two numbers, a int and b int, returns an int. This is going to act a little weird for you because integer division will only return integers, but we'll ignore that for now. But one important thing is that b might be 0 and you can't divide by 0. So we can do something like if b equals 0, we can return, I don't know, 0, which is not really correct math. And otherwise return a divided by b. So let's try a couple things here. We'll do print divide two numbers. We'll divide 4 by 2. And then let's try to divide by 0, divide two numbers, 4 by 0. And we expect to get what? 2 back from this and 0 back from this. This is not real math, but we're protecting ourselves from a possible crash. So 2 and 0, and that's correct. Let's talk a little bit about strings. So strings are a very useful type in Godot because they represent text, words, letters, or paragraphs. They also are often used as kind of keys. Maybe if you want to check if a certain animation is playing or an input is playing. Often when they're used as keys, you see them as string names, which look like this, which just means that they're harder to change, but we're not going to handle that right here. Strings work fine. So a string is just a value that's text like that. There's a couple things you can do with strings. In fact, many things. I'm going to show you a couple here. So you can concatenate strings. So var new string equals hello, and then you can put another string here, and this will make the variable hello, my friend. You can concatenate with variables, which is actually much more useful. So you can say var name equals, we'll name this person Terry. And you can say hello plus name. I want to make sure these are properly typed. And then if we print new string, we'll get hello Terry. Why is name angry at me? Oh, sorry. Name is already a property on every node 2D. So let's call it something else. We'll call it friend name. Should be better. Hello Terry. Okay. There's 100 other things you can do with strings. I think we'll get to them later, but I want to give you a little challenge here. So your challenge is to create a function called merge strings. It should take in 3 strings. String A, string B, string C. It should return a string that is those 3 strings concatenated together, and you should print it onto the console after it is returned. Okay, you take a second and try to do that challenge, and then you can see how I do it. Okay, cool. Welcome back. Let's see. So if you remember, we need to create a function called merge strings. So let's do that. We'll do it right here because it doesn't matter where we define the functions in our code. We'll do func merge strings. Now, this function signature is important here. So what do we want here? Remember, we want the function signature is quite important here. Remember, we want to have 3 arguments. So string A, string, string, and string C. You'll notice that this is quite long, so we can actually do returns and put them on different lines here. That'll work. And then we like to put 2 indents when we are doing these kinds of different lines, just to make it different than the single indent that's going to go down here. And we want to make sure we return a string. So if we write pass here, we get an error saying not all code paths return a value, which is good because it means that it is trying to get a string out of this and getting nothing. So if we return that looks okay. The warnings we're getting here are because we're not using these yet. So that's fine because we are going to. So let's return string A plus string B plus string C. Okay, now it is working great. Remember, there's 2 indentations here, back to 1 because we're inside of the function. And then let's try to call this. Let's do merge strings. Hello. You put a comma between every argument. Subscribe to on YouTube. Okay, cool. So what's this going to do? Well, this does the function, but it isn't putting the return value anywhere. So we can put it into a variable, var merged string, and then we can print merged. And it would be totally okay to not put it in a variable first and just put merged strings inside of print. Totally fine. Okay, let's run this and see if it works. Hello, subscribe to Hovering Skull on YouTube. There's no spaces, so if you want to make that work better, you can put spaces there. But hello, subscribe to Hovering Skull on YouTube. Wonderful. Okay, so that's enough subliminal messaging for you. Yeah, so now I think you have a kind of understanding of variables and functions and types. So this gets much more complicated. Every section after this gets a little bit harder, but I think this gives you a little basis. All right, let's talk about the Godot scene tree and Godot nodes. So everything that renders and does anything in the world of a Godot scene is a node. And let's try that out. I'm going to make a new scene in sample scenes. We'll call it Godot nodes. Here we are. And here we have on the left side our current scene tree. Even if we're doing all of our work in code, the only way to get Godot to render sprites or play sounds or run timers or run the ready and process effects is to add things to our scene tree. So we can go up here and we can right click, and if you click on add child node, you get a big list of every node that's in Godot. So we can go in here and there's a search up here, but let's just find a sprite node. You can see if you open up Node2D, you see all of these different types of nodes that are descended from Node2D. And let's see, they have animated Sprite 2D. I want to find Sprite 2D. Where's that? 2D. Sprite 2D. Click on create. And now we have it in our tree. It's a child of Godot nodes, and it isn't doing anything because it has no texture. So if you click on this here, you can see on the right side here, it says texture empty. Just for now, click on this and click on noise texture. And you can see we now have this big, ugly pink box. Now, a Sprite 2D is a type of node that is meant to render a picture, pretty much, a 2-dimensional picture. So let's get a picture that we can use here. I'm going to go to kenny.nl. Kenny is a creator of assets that makes a ton of cool assets that are all free to use, and you can even release games with them. Go to kenny.nl/assets. And then I want you to search up, I think it's called Pixel Platformer. Cool, I think. Take the first one here, Pixel Platformer, and click on download. You should donate if you enjoyed this. I already have. And then you can download this to your download folder. Okay, once that's downloaded, you can open it up, go into your download folder, and you want to extract all, and we can add some images to our Godot. I would take this whole folder here and just click and drag it right into your Godot, and you can put it wherever you want in the file tree. I'm just going to make a new folder called imports, and I'll drag that in there. Okay, anyways, now we have a bunch of images we can use. And so now we can go back to our Sprite2D node here, and I'm going to find something in here. I think characters is good. And I'm going to move one of these things, tile 0000, into the texture. And there we go. We got a little guy on the screen. And I'm just going to move him. You can click and drag and put him somewhere in the screen. And then if you play the scene, you'll probably get, that's the last scene. Remember, you have to find your scene, right click, set as main scene, and then play. And we got a little guy on the screen. So this is a Sprite2D node. Because this is a tree, you can add as many nodes as you want as children under nodes. So if I add another Sprite2D that's a child of Sprite2D, we could, let's see, we could give it a different image and we can move it around, and we have these two here, but since this is a child, Sprite2D, we'll call this Sprite child. Since this is a child of the first one, if we move the first one, it moves its child too. So this is one of the properties of children in these nodes, is that they have positions that are relative to their parent. Scenes always have one root node that can have as many children as they want, and every node can have as many children as it wants. One quick thing I'm going to do here is, notice these are a little bit fuzzy looking. I'm just going to quickly go to project settings. I'm going to rendering textures, and where it says default texture filter, change that to nearest, and it will make your pixel art sharper. And now look, that looks way better, huh? Play, there we go. So when we play anything in Godot, we're playing a scene. A scene always has one root node and can have as many children and as many layers of hierarchy as you want. Yes, this is very confusing at first, but you will get used to it. We've been doing this in the visual editor, but you can do all of this in code also, and there's good reasons why you'd want to do that. We will get to that soon. Godot comes with a ton of different nodes that you can use to do lots of things. You can have audio listeners, you can have bones, which are used for animations. You can have a camera that you can move around, which controls the viewport. You can have collision shapes and stuff, which I won't cover in this video, but are really useful for physics-based games. And all of these ones that I've talked about are all children, or at least inherit the functionality of Node 2D. You also have Node 3D, which is used for 3D worlds. It's got its own versions of a lot of these. And control nodes are what's used for most of our UI setups. And whenever we make a class that extends our a node class, like Node 2D, like we've done with a bunch of things, like our, let's see, like variables and functions here, we are then able to access it as a node. We can make a new variables and functions from our last script and add it to this scene. And it will run its functions, its process, and it's ready. And we can use it like we would variables and functions and treat it as a node. We can put it as a child of something else, etc. Everything that has functionality in the scene of a Godot game is a node, but all the primitive types like integers and strings and vectors, which we'll see soon, are not nodes. Those are just primitive types. When you make a script, and we'll make a script for this now, you can choose to inherit Node 2D. You could inherit any other type of node, or even any other type of data type in your whole program. And when it says extends Node 2D, we can now know that we're able to add this to our Node 2D scenes and do things with them. Okay, cool. So now we're in a new script called Godot Nodes. Let's see how we can actually manipulate this scene from code. So if we want to add a new, so let's add a sprite to the game and position it when we start the game. So we can make our ready script here, and let's add a function to it called add sprite, and we'll make a add sprite function here. Now, what do we want to do here? Well, there's a few things we have to do. For one, we need to actually create the sprite object. I'm just going to go to 2D mode here and delete all of our placed sprites so we can see this better. So in add sprite here, we need to do this. We'll go var sprite 2D is a sprite 2D equals sprite 2D dot new. This creates a new sprite 2D object. And then we can do add child sprite 2D. Every node based script has add child, and this just adds it to the tree under it. Now, what's going to happen when we play this? Well, it looks like nothing, but if you click on remote over on the left side over here, you'll see it shows you what's currently happening in the game. You can see Godot nodes, and you can see underneath it a sprite 2D node. The reason it's not showing up is we don't have a texture for it yet. So let's add a texture to it. There's a couple ways we can grab one. I'm going to use preload. I won't go into this too deeply, but it lets us preload a file resource. So we'll do var, we'll say sprite, or we'll say our character texture is going to be a texture 2D equals preload. Preload runs when this script is loaded, so it doesn't have to run every time we use it. Preload, and we're going to preload. What we do is right click on one of these character tiles in the bottom left, click on copy path, and then put 2 quotation marks and put that between them. So this will get us a reference to that texture that's living in our file system. And then from here we can say sprite2d dot texture equals character texture. And this is the dot notation I was talking about before. Sprite2D has a property, a variable in it called texture, and you can set it by doing sprite2d.texture and passing in the texture we want. So now if we play this, you see we've got a little guy. He's up in the corner because we have not changed his position yet. Let's do that. We'll do sprite2d.position equals, and we're going to cover vectors when we cover math, but I will show you them a little bit here. Positions are always based on vector 2s, which are pieces of data that have an x and a y component. The x is the how much to the left or right it is, and the y is how much up and down it is on our screen. And to make one, we do vector 2, and then we give it 2 numbers. We can give it 50 and 50, and then we can play again. And we'll see he's a little bit moved around. Let's just play with that super quick. I'm going to go back to 2D mode. I'm going to make a new sprite, and I'm going to give it a tile or a image, and we should be able to see, there he is. Here's our sprite. If we look at transform in the inspector on the right hand side here, and we move him, you'll see how the position changes. If we move him to the right, the x goes up, left, the x goes down. If you go up, the y goes down, and if you go down, the y goes up. And if you go to the bottom right of the screen, they'll both get bigger. And this is because this is just treated like a big grid, and it should be pretty easy to get used to this in 2D. Just think of it like a grid. And yeah, now one thing we might want to do here is actually keep track of the sprite once we add it. So we could return. So we'll do var sprite equals add sprite, and we'll do return sprite2d. Now we have a reference to this, and with the reference, we're now able to do some other things with it, like we can destroy it. So if we want to remove any node from our scene, we can remove child the node, but also we can queue free the node. Queue free means, it'll be sprite dot queue free. Queue free means that we destroy it from memory at the end of the frame. Remove child means we remove it from the scene. And queue free should be enough most of the time. So if we play this, I'll remove the sprite we've got. If we play this, we shouldn't see anything because within the same frame, we are creating the sprite and adding to the scene, and then we're destroying it. We have a few other things we can do, like we can do something like get children. This will give us a list of every single child that is underneath our node. If we do print get children and play, it'll show us that we have 1 sprite. If we do that again after we queue free, it'll probably still show us we have 1 sprite because queue free doesn't happen until the end of the frame. Yeah, if we change this to just free, look, it shows that you have nothing in the second call. So that's something you can think about. Really, we use queue free because sometimes things try to access something in the same frame, and it breaks if you try to access something that's been freed like this. Don't worry about that too much right now. Let's also, while we're dealing with sprites, we should talk about z-index. If we go to our 2D world here, and we add 2 sprites, we'll add one that's this guy, and then we'll move him around, and then we'll add a new sprite, and we'll make it a ground tile. You'll notice that they render in the order that they are in the hierarchy, and you might not always want that. Maybe you want your characters to always be above the background ground. One thing you do for that is change the z-index. So go to the sprite you want to change, go to ordering in the inspector, or in code, it's just .z-index. And then we just put z-index to be higher than the default 0. We will probably use this in the game we make. So you can access z-index really easily. You can do sprite2d.z-index equals whatever you want. You can even do negative numbers if you want it to be behind the default. Okay, challenge for you. I want you to create a new function called add custom sprite. It takes in 2 arguments. It takes in a texture variable and a vector 2. Render that texture on screen at that position. Cool. That shouldn't be too hard with what you know, so give it a shot and check my answer after. Okay, so let's try this out. We want to call it add custom sprite. Add custom sprite. Sprite2D. Actually, we don't need to return it. That's not part of the contract we got here, so we can just do void. And we need to give it 2 arguments. Argument 1 is going to be texture, texture2D. We saw that up here. And argument 2 will be position, vector2. Okay, then we can indent under here and start writing our function body. Basically, we want to do the same stuff as we did in add sprite. So we'll do sprite2D. Sprite2D equals sprite2d.new. We'll do add child sprite2D, and we'll do sprite2d.texture equals, well, we want to use the texture we're passed in this argument, so we'll do that. Sprite2d.position equals, well, we need to use this position from the argument, and that should just work because we don't need to return it and we're not going to set the Z index. So why is it mad at me? Oh, it doesn't want me to use the word position because that is a word that's already on nodes as a variable. So we'll just use sprite position. Cool. Add custom sprite. Okay, cool. Let's call it now. So we'll do add custom sprite, and then we want to give it a texture. Let's preload a new one. So I'll do var new texture, texture2d equals preload. And if you remember, we just need to put quotation marks, find the texture we want, copy path, paste it in, great. And then we will say add custom sprite, new texture, and then vector2, and we can do 100 and 200. And why don't we do it again too? This is how functions can be really useful because you can reuse them a lot. So we can do one with our old texture, and we can do that at 650, 320. Let's play and see what happens. We're now rendering 3 guys on screen here, and that's because we already put 2 on the screen here, and then we're adding 2 more. And then if you look at remote here, you can see we have the 2 sprites we already added, and then the 2 we added in code there. Great. Just another thing to touch on that I already did kind of is that, remember, every single node 2D has a transform here that has a position, rotation, a scale, and I guess a skew, which I don't use very often. But the important thing about that is that if it has children, and I'm going to make this tile a child of this one, the transform affects all of their children. So keep that in mind. This can be a bit confusing. If you need to have something be a child of something that has a position, but still have the same position in the world, you can use .global position. Looks like .global position like that. And that will ignore the parent's positioning. I'm not going to do much with rotation in this set of videos. It gets a little more complicated because you need to understand trigonometry a little bit. Yeah, position we're going to be messing with a bunch. The other thing that is really important about the nodes in the scene is they are what handle like physics calculations too. So in a lot of games, you might want to handle collisions using nodes to have like gravity and forces and like walls you can't walk through. I'm not going to handle that in this video. Physics is another layer of complexity that I don't want to mess with right now. That can be in a future video. If we were doing a physics game, like a platform with physics, we could just put forces on characters to move them around. But in this, we can just edit something's position to make it look like it's moving in the world. Okay, one last node I want to cover is the camera. If you do not put a camera in a Godot scene, Godot makes a camera up for you and puts it right here. You can see this green line, or sorry, you can see this blue box, kind of, right? But if you do add a camera, we'll do add child node, Camera2D, you'll see it actually moves to this pink box here. And then if we play it, you see that we're kind of offset. The camera, you can move its transform here. You can see you can give it like 400, 600. And then when you play, the camera will be offset by that much. And this is how we can move the camera in game too. And that lets us, you know, simulate movement around a space, right? Okay, otherwise the camera works the same like as any other node. It's got a transform here. You can use the same methods on that. You can create a new camera with something like camera2D equals camera2d.new child camera, and we can do camera.position equals vector2 3. If you add 2 cameras to a scene, I think if you put multiple cameras in the scene, it will default to using whatever the first camera in the hierarchy is. So this won't do anything. But if we remove this camera and run this, we're going to be somewhere where there aren't any sprites to look at here. And just remember, if this isn't working, make sure you've added it as a child to something in your scene, or else Godot will not use it as a camera. Okay, terrific. Let's move on to math. Okay, I'm sure you're really excited to talk about math now, so let's make a new scene. We're going to go to sample scenes, right click, create new scene. We'll call it math, and then we'll double click on that to go into it. We will go to select math up here, press create new script, and we will call it math.gd. This is pretty exciting. I love math. I hope you do too. So we're not going to get crazy with like very advanced math here. Everything here is stuff you'll probably understand from, you know, early high school. It's nothing too fancy. So let's make our ready function here. This of course runs at the beginning of every scene, and let's make some variables here. So we'll make a variable called a, and that'll be 4, 5. Okay, typo, but it's fine. 5, and we'll make a b, and it'll be 10. We can do some things with these two variables. We have all of our normal arithmetic operators that you're used to. So var sum equals a plus b. You just have to do a plus. You can guess what this is going to be. It will be an integer. We can do var difference int equals a minus b. We'll do var product equals a times b. The star is what we use for multiply. We'll do var quotient equals a divided by b. And it's this, the backslash means divided. And let's just put a return here so we have something to debug to. I'm going to put a debug flag on return, and we'll play this. I'm going to make it the main scene. Press play, and you'll see we have variables here: a sum of 15, difference of -5, a product of 50, and a quotient of 0. Wait a second. Why do we have a quotient of 0? 5 divided by 10 is supposed to be like 0.5, right? So 0. So why is 5 divided by 10 0, not 0.5? Think about this for just a second. It's not necessarily intuitive, but maybe you have a guess why. Yeah, it's because we're making this an integer. And when we make this an integer, we cut off any decimal place stuff and just default to the integer value of it. Now, if we want to actually do a float division, we can do something like this: equals a divided by b. Now, let's see if this works. We'll print it. I'm going to play, and we'll look at our output. Forgot to close our parentheses. Great. Anyways, if we play this, we get 0.0 again, which is, again, not what we want. The problem isn't that we're putting it into a float. The problem is that we are dividing two integers. So one quick fix for that is to just turn one of them into a float. If you put the word float as a function and put in one of these values and then play it, it should work, and you get 0.5 as expected. You need to make sure that you turn one of the values into a float. Now, this will get you all the time. Just be aware of it. One more cool operator we can do is the modulo. We talked about this a little bit before. It looks like a % sign, and what it does is it gives you the remainder if you divide one number by the other. And I'll show you what that looks like. We'll do var remainder equals b modulo a, and let's print that. What do you think this is going to be? I think it will be 0 because 5 goes into 10 twice with no remainder. Let's just check. Yeah, 0. What if we do a modulo b though? It should be 5 because 5 doesn't go into 10, or 10 doesn't go to 5 at all. There you go. Remember before, we used this to check if a number was even, because if you divide anything by 2, any integer by 2, and there is a 1 left over, you know it's not an even number. Another really good use case for modulo is if you're doing math with a clock. Say you have 12-hour days or 24-hour days, say, and you want to add to that. All we do to get the value in time is just get the modulo of the addition. Let me pose that to you as a challenge, and you can kind of think about this and get some more intuition with it, because it is a day-to-day use case of a modulo. So here's your challenge. So we're going to make a function that takes in a time. So in like 24-hour clock, and it'll just be the hours. So something like 11 or 13 or 6 or 2 or 23, and another time, and adds the two together and tells you what the new time is going to be in a 24-hour clock. So if it is 2300 or 11 o'clock p.m. and you add 5 hours to that, we end up at 4 a.m. So you want to give back 4. If it's 1 a.m. and you add 6 hours to that, you just give back 7 because we don't go over that 24. So make that function for me. And if it's confusing or you're not European and this is new to you, I don't know, man. It's a little more challenging than the other ones, but yeah, let's give it a shot. Okay, we'll make a function, func adds time, and we'll say current is an integer and add is a integer too. It returns another integer, which is going to be the new time. What do we do? Well, we do current plus add is what's going to give us a number that might be over 24, right? But then we can put this in parentheses, which I haven't shown you before, but maybe you can guess because that's how math often is written. You go modulo 24 because we know this is on a 24-hour clock, and that should give us a number, and all we have to do is return that. So let's try that out and see if I didn't mess that up badly. Print add time 23 4. We expect this to be 3. Print add time 11 5. We expect this to be 16. Print add time, say 1 and 23. We expect this to be 0. Let's give this a shot. If I run it and play, I get 3, 16, and 0. Which is correct. Hopefully that one wasn't too confusing to you. I think it's a good way to get a little bit of sense of why we'd want to use modulo. There's lots of other reasons too, but that's kind of the everyday use case, I think. Let's go back to something we did a little bit of in nodes, but we want to cover again. We'll talk about vectors. So vectors in Godot and many other engines are a special type of data structure that is made up of a certain number of components. We're going to use vector 2's, which are made up of an x and a y, which are both floats, and vector 2i's, which are made up of an x and a y, which are both integers. So we can create a vector 2 called v2, and we can create it by just typing vector 2 as a function and giving it 2 numbers. Sorry, like that. v2 is vector 2, and then you put it parentheses, you put the 2 values, and you can pass this directly as a position to a sprite, for instance, or a bunch of other things too. It has a integer only cousin, vector 2i, which works very similarly, except for the components x and y have to be integers. Now vectors have some really useful and important functionality and mathematical properties. We're not going to go over all of them, but there's 2 I want to show you. The first one is that you can add 2 vectors. So our sum vector equals v2 plus, let's make a new one here, 55, 100. And you don't actually have to put the 0.0. It will turn this into floats for you because vector 2's always use floats. And we can print sum vector. Have a quick think and tell me what you think this is going to equal. So we have v2, which is 40, 50. We're adding 55, 100. So once you have some thoughts about that, you can run this and you'll see 95, 150. That is 40 plus 55 and 50 plus 100. You just add the x to the x and the y to the y. And we can quickly debug here to see what a vector 2 looks like. So we have our v2 here, and a v2 has a x and a y component here. You can do the same thing with 2 vector 2i's. I'm not going to show you, but try that out. The other really important mathematical property of vectors is you can multiply them by a single number, a scalar number, like a float or an integer. So I can do scaled vector equals v2 times 10, and let's print that out. So think about what you think this would be. We have v2 here, 40, 50, and we multiply that by 10. This is not a trick question. Just guess. We'll run this. 400, 500. We just multiply each of these numbers by whatever we multiply it by. Maybe it's not super clear why we would use any of this stuff, but I promise it is useful, especially for positioning stuff and moving it on screen. So let's do that. I want to here create a sprite, and then in process, I want to move it across the screen in various directions. So let's do that. I'm going to create a sprite in a variable outside of our ready function so that it's accessible within our process function. So we'll say Sprite2D, and we covered this in the last section. So go back if you want some refreshers. And then we will down here say Sprite2D equals Sprite2D new. We will add child Sprite2D. Let's give it a texture. So remember, we can preload images. So var texture is a texture 2D equals preload, and then we're going to grab one of our little alien sprites, I guess, paste that in. Okay, sprite 2D dot texture equals texture. Terrific. Why does it not like this? Sprite 2D. Oh, right. I put an underscore here. Okay, cool. So now we have a character on the screen. Let's put him somewhere near the middle of the screen. We'll go sprite 2D dot position equals, and then we want to create a new vector 2, 300, 300. And let's just make sure this is working. We will play the scene, and there he is. Cute little guy. Cool. There's a problem here, and that's that this guy is not moving. So let's do that. Remember the process function that we had before? Let's create one here. We'll create it after ready, but it doesn't actually matter. So func process, and Godot should give you some autocomplete here. We want this, enter and indent. So because our sprite 2D is declared outside of ready at the top here, and we can just click on this arrow to hide ready, we can access it within process. So we'll do sprite 2D. What do we want to do here? Well, we can do something like position, and then we can do equals sprite 2D dot position plus some vector. So vector 2, 10, 10. And let's see what happens now. He just zooms off, which is a good start. There's a quick little little shortcut for this. Instead of doing this equals this plus that, we can just do this plus equals that. And this should work exactly the same. It's saying, hey, take this and then add this to it and assign it back to this value. Same thing. There is a problem with this though, and that's that this is always going to move this much every frame, even if the frame has a different delta. And if you remember looking at the deltas before, they actually vary quite a bit. So the way to fix that is we multiply by delta. Now, delta is a very small number. It's usually 0.016 repeater. So this is going to slow us down, but it will be always smooth. Cool. So the way to fix that is by multiplying it by some constant. And we'll call that constant speed. Let's add it up here. Const character speed equals, oh, good. We'll play. Zoom. There he goes again. Great. What if we wanted him to go in the other direction? Well, that would just be minus equals. Zoop. There he goes. So it's pretty easy to move things on screen. You just need to multiply that by delta and make sure you scale it by some sort of value for speed, or else it will be very slow. There's a few more conveniences we can do here. Vectors also offer a few built-in conveniences. So built-in vectors, we have vector2.1, which is equal to 1, 1. We have vector2.0, which is equal to 0, 0. We've got vector2.right, which is equal to, I believe, -1, or no, 1, 0. Left is -1, 0. We have up, which is 0, 1, or 0, -1. And we have down, which is 0, 1. And then there are vector2i versions of all of these too. So vector2i dot 1 is also 1, 1. It's just this is actually 1.0, 1.0. Okay, so why are these useful? Well, because now instead of making a new vector here, we can do vector2, 1 times delta times character speed, when we just need to make character speed a bit faster, like 500. Zoop, and there he goes. So this just makes it even simpler. And it's a really common way to do things. So your challenge, make the guy just go to the right, not up and down at all. It should be pretty easy. You just have to change something in line 51 here. So good luck. Okay, cool. So what I would do here is I'd make sure this is plus equals, and then we want to find vector2 right, and then let's run it. There he goes. Really easy. And the reason why this all works is because sprite 2D position is a vector 2, and we can add things to it. We can multiply the things we add and do this math to it. Next thing I want to cover here is the issue of floats versus integers. You might be thinking we've got integers var a equals 1, and we've got floats var b float equals 1.0. Why don't we just do everything? These are reused. We'll call it the ziz and zaz. Why don't we just do everything with floats? Because they're more expressive, right? We can have these, you know, partial values. We can have 1.5, 1.6, 1 point that, whatever. Integers can only be 1, 2, 3, negative 543, etc. Why don't we do that? And I'll show you why that's kind of a problem. And it's a problem that gets to a very weird thing in how computers work. And that's that we store floats without full precision. To show you how that works, I'm going to say var f1 equals 0.1, float equals 0.1, var f2 float equals 0.2, and then var expected sum is going to be a float equals to 0.3. If we add 0.1 to 0.2, we expect this to equal 0.3, right? So let's do that. Var real sum equals equals f1 plus f2. And then what we want to do is print expected sum equals real sum. Let's also print expected sum, and let's print real sum. So this equals, if you remember, is going to tell us if these are the same number, and it will print true if they are. Let's play this and see. Okay, so if you see at the bottom here, we get 0.3, 0.3, and false. Even though these both say 0.3, they are not the same number. And that's a problem because floats are imprecise. And if we expect things to be equal after doing float math, sometimes they will be, and sometimes they will not be. This number is being truncated by Godot to only show the 0.3 for the real sum, but it's actually 0.300000001 or something like that. It's just ever so slightly off because floats, again, not precise. For anything that doesn't matter that much about exactitude, like positions on a screen, this doesn't matter. But if you ever have to compare two values to see if they're exactly the same, it really, really, really matters. And so for that reason, we use integers whenever we want to check if things are the same. And that's why I tend to like to work with things on a discrete grid. Like imagine a chessboard. We don't care exactly where on each square your pawn is. We just know it's on that square or it isn't. So something like var int sum, this will always be 3 and it will always be equal to 3. So this is something that's going to be relevant to the game we make because we are going to want to deal with things as integers. A couple more math things I want to throw your way before I give you a challenge. Rounding. Godot includes features for rounding. We have round I and round f. This rounds something to a nearest integer to the nearest float. So we can do print 0.3, or we can do print round I 0.3. This will round this to 0. Print round f 0.3. This will round this to 0.0. Let's play these. As you see, 0 and 0.0. We also have things, we have ceil I and ceil f for integers and floats, round up to the nearest integer. And note that even though ceil f is rounding to an integer, it is going to give you the float version of that. Floor I and florf round down to the nearest integer. And then we have a bunch of other cool things. We've got abs I, abs f, give you absolute values. And we've got things like clamp. I'll just show you quickly with clamp what we can do. So if we look at our screen here, our boy runs all over to the edge there. We can make it so he stops at one side by using clamp. And I'll show you that quickly. So we'll go to process here. I'm going to comment this guy out and we're going to clamp it. So what we do for that is sprite2d dot position equals, and we can't actually do the plus equals for this because clamp has to be a function in here. So there'll be vector2, and we can build a vector2 here from different things. And the x is what we want to clamp. So we'll do clamp f, and we'll make this sprite2d dot position dot y, so we keep the original y value. And in clamp f, it takes 3 values. One is the actual value. That's going to be sprite2d dot position dot x plus whatever amount we want to move him. We'll say speed times delta. And then we can give him 2 values here. These are the things it has to be in between. So we do 0 and 1,000. And that will make it so he stops at 1,000. This is getting a little long. Sprite2d. There we go. Something gets long like this, you can actually break the line by putting a slash and enter. And then you can a slash maybe after the comma and enter, and then you can indent it. And this will be treated as the same thing. So we'll do that here too. Cool. So what we're doing here is clamping this float between 0 and 1,000, but we're still doing that same math on it. So you should go over there and stop at 1,000. It's a little bit hard to read, but that's what clamp's doing. And then if we want him to go the other direction, he should stop at 0. Let's try that with a minus, and he stops at 0 right there. Cool. Okay. So the challenge I want you to do now, using the tools that I've given you, create a function that takes in a vector2 and returns a vector2i with all of the vector2's components rounded up the nearest integer. Okay, think about how you would do this, and then I will show you in a moment. Okay, let's do this. Let's do round up to v2i. It takes in a vector2 and it outputs a vector2i. What happens here? Well, we want to return a vector2i, and it's got two components. The first one is going to be the x. The x is going to be what? Well, we need a function for this to round the x of v2. So we'll do, I see here we have CLI and CLF. We want the integer version, CLI v2.x, and then comma CLI v2.y. Okay, let's print this off. Just make sure it's correct. We'll do print round up to v2i, and we'll give it 23.4 and 19.9, and oh, this has to be a vector2. And then we'll do one more to see a different value, 1.0 and 11 something. Cool. Let's see if this works. We're going to run this. We get 2420 and 112. 2420, 1. It's rounding up. All right, this is really useful because, well, if we create two that look like this through different means, they may not be equal. We can check equality very easily on two vector2i's. And that's going to be how we detect collisions and where our guy is in the game we're going to make soon. Okay, we're almost done the math section. Last math thing is randomness. How do you feel about RNGesus, the random number generators? We can do that really easily. We have functions for that. So if we want to generate a random integer, which is something we probably often want to do, we can do randi or randi range, and you can do a from and a to. So we'll do 0 to 10. And what does this say? It's inclusive. So you can get any number, 0, 1, 2, 3, all the way up to 10 here. And you can also do random float equals randf range 0 to 10. And note, we can just include these as integers. This is the same as doing 10.0. Let's print these off, and they should be different every time. So 9 and 9.08, run again, 1.61, run again, 2 and whatever. Anyways, this is great. This is how we do a random integers. If you want to simulate like a coin flip, you can do something like coin flip float. Oh, well, it's going to be a Boolean, say. We'll do randf. So randf is a special one that gives you a number between 0.0 and 1.0. We'll do that equals greater than 0.5. This means greater than. So if this number evaluates to greater than 0.5, this becomes true. And so let's print our coin flip. Play, false, true, 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 true. I'm getting pretty lucky. True, false. So again, simulates a 50% chance because this makes a random number between 0 and 1, and we check if it's greater than 1/2. Okay, I think that's enough for math for this. You may need to watch this again, but I hope you can get your head around it. I know some of the clamp stuff especially looks a little confusing, but just understand we are creating a vector2 here. The x here is going to be constrained between 0 and 1,000. Okay, wonderful. That's the end of the math part. So we can do something else, and soon we'll get to the fun part. Just kidding. This was the fun part. All right, let's make a new scene, and we can go back and do some more advanced control flow topics. Fun. Sample scenes, create new scene. We'll call this advanced control. Double click to open it. While we're down here, let's right click, set as main scene. And then up here, add script, advanced control. Here we go. So a couple concepts I want to cover here. Let's make our ready function here. You should kind of remember this by now and hopefully be able to reproduce it at least fairly accurately. Let's pass it so it doesn't yell at me. Here we go. So let's talk about conditionals again and Booleans. So if you remember, a Boolean is a variable, a type that can be false, or it can be true. And when we have an if statement like this, if you recall, if Boolean, we'll just name this something else like my Boolean, so it's clear that's not the type, we can print hello. Now we have this thing here, Boolean, and if we play this, maybe guess what's going to happen. We just get the hello, and if this is false, if you remember how the control flow works, we start here, we go here, check if this is true. It's not, so it doesn't go into this. So nothing happens. That's correct. If you recall again, we have else, which we can do print goodbye. We get goodbye. And there is a secret third thing, elif. And elif lets us put in a different Boolean here. So var another Boolean, bool equals true, and we'll say please send help. What do you think is going to happen here? We have another Boolean true and my Boolean false. So what's going to happen is we'll go to this one, check it, false, check this one, true, do this, and we'll skip goodbye. Please send help. Terrific. There are a lot of ways to actually make Booleans though, and I'm going to show you a few of them. So let's have some integers here. So we have numerical comparison operators. They work on integers. They also work on floats, exactly the same, and you can compare integers to floats. We can do something like this. If a greater than b, print hello. If a equals b, print please send help. Otherwise, print goodbye. So what's going to happen here? Well, it's going to check this. A is not greater than b. It's going to check this. A is not equal to b. It will give you goodbye. That's right. We also have less than, hello. And we also have versions where there's an equal sign, so it captures if it's equal or not to. And then there is not equals, like this. So since these are not equal, hello. Now what's happening here is when we hit this part of the code, it evaluates this expression and it turns it into true, and then it runs this. And this happens kind of recursively. So we can always take one of these expressions and chain it with something else. We can use that, and we can do that with something like and, which will check if this is true and this is true. So if we run this, we get hello. What if we turn this to false? Well, this turns into true, and we have if true and false. This is a formal logic construct, but for something to be true of an and statement, both sides have to be true. So this becomes false. This gets skipped, and then we go to goodbye. I'm going to remove this for now. We also have or turns into true if one side is true. So if we do play this now, we'll get hello, because this is true, and it doesn't matter that this is false. And we also can do things like not. And if you put not before something, it flips whatever this is. So this evaluates to false, and not false equals true. It print hello, or goodbye, I guess. If not A equals not equals B. Oh, this is true, and then we flip it to false. Right. We can get as complicated as we want with this. You might see something like not that and 43 less than equals to Z and whatever. And all we do is go through that same process and reduce each part into a Boolean and compare it in that way. It can get really hard to read, and we're not going to do anything too complex, but we can do that. Often you're going to see a conditional to check if something is null. So let's make a nullable type here. So var sprite, it's going to be a Sprite2D. These default to being null. Remember, integers default to being 0. You can't make them null. We'll do if Sprite2D, or if Sprite equals null, return. And then after that, let's try to print something. Print Sprite exists. So what do you think is going to happen here? You're getting a warning here because it knows you never assign it, but that's fine. If we play this, are we going to ever print Sprite exists? No, because we get to this, we see the Sprite's null, and we return. This is really useful because sometimes we need to check if something exists before we do operations on it, like change its position. So now we can do sprite.position equals vector to something. And we play this, nothing happens. If we remove this guard, we get an error because we start trying to change Sprite's position, but Sprite doesn't exist. Now, remember, every single time we do something with a comparison operator like this, or like this, or the greater than, less than, that, it reduces everything to a Boolean and then evaluates it as true or false, and then does what it says next. So yes, it gets complicated, but really the rules are quite simple. And we can nest these expressions infinitely. Let's look at something else. I'm just going to comment this out so that we don't return too early. Let's talk about collections of things. Now there's two basic collection types in Godot: arrays and dictionaries. So var myArray is going to be an of type array, and you can give it a subtype saying what type of thing is in the array. Equals, and then we put 2 square brackets, and then we can put some elements. And an array is just a list of items that are ordered. So they're ordered starting at 0, 1, 2, 3. In most programming languages, you start counting from 0. And we can always access the 0th item or whatever index by this. Print myArray and use square brackets 0. Print myArray square brackets 1. This is going to give you the 3, and this will give you the 4. Let's play this. 3, 4. Dictionaries are a bit different. So myDict is going to be a dictionary. Dictionaries take 2 subtypes. One is the key and one is the value. So a key, we can make a, let's say a string, and the value will make a integer. We'll make it equal. And then we make a dictionary literal by doing 2 curly brackets or squiggly boys like this. And then we have to do the key type, which is a string here. So we'll say, oh, I don't know, strength. This could be like stats for a RPG. We put a colon, and then we put a value, comma. We'll do dexterity 43, moxie 43. And then when we want to access these, we access them by the key. So we can do var strength equals myDict, and then we can put strength. This finds whatever item is in your dictionary that has the key strength and returns this value. So let's print strength 23. 23. Now we can put new things in both of these too. So let's see. So we can do myArray.append 20. This will put a 23 on the very end of this, and then we can print myArray. If we play this, we get what we expect. You can also like pop the front value off of it, like pull it off. We can say var value equals myArray.pop front. This does is 2 things. Is it removes the first element from the array and puts it into this variable. So if we print front value here, and if we print myArray here, we will see that we now don't have a 3 in this array. We also have pop back too, which will remove the 23 at this point, right? Cool. And then you can directly write array elements with myArray like 2 equals 44, 4, 5, 44. I guess that's what it's supposed to be. Right. And in our dictionary, we can also write to it with, myDict dexterity equals big number. That will work fine too. We can check the size of either of these collection types with .size. So print myArray.size as a function, and we'll print myDict.size as a function. They both are 3 at that time, which I think is correct. And there's lots of other ways you can go through and filter and map over these values, which I'm not going to get into because we don't need to yet. But what I do want to do is show you how you can loop over one of these. So remember loops from the first section. We can go for I in myArray. So before we did range, and then we did like some numbers, you can also loop over elements in a collection. So for I in array, and then we can print I. So we'll see. What do you think this is going to be? It'll probably be 4, 5, 44. 4, 5, 44. We could even use this to sum something up. So we'll do var sum equals 0, and then we do sum plus equals I, and then we can print the sum at the end. And you'll see we can get a sum of every element in the array. It should be 53, I guess. And you're not limited to strings and ints. You can make arrays of anything you want, any single type. You can make an array of Sprite 2Ds, of cameras, whatever. The type system is flexible. There are some interesting performance reasons why you would choose one of these over the other, but I'm going to leave that for now because I don't think it's that important at this level to understand them. Just to let you know that every operation on these kinds of data types has a different cost in performance that can really add up. And that's something to talk about later. Cool. Let's talk about accepting input. And I mean input, not for like feedback, but input from a controller or a keyboard. So we're going to do this in a process function. And input is actually dealt with by a conditional. So we're going to do something like if, and it's going to be like pressing the button. I'm pressing the button. So we just need to figure out what this is supposed to be. And we can set up inputs for our project by going to project setting, input map, and let's click on add new action. And we're going to say, we'll say this is action button. We'll add. That adds an entry to this list. We press plus, and then you can press any button on your keyboard or your gamepad or whatever. I'm gonna do spacebar. Press OK. Now action button is mapped to space. We close this. And then here we can do if input is action just pressed, and then we can select action button. So let's see that working. I'm just going to press play. And if we press space, you're going to get I'm pressing the button once. If you remove just here, it's going to keep firing as long as you've pressed it. So try that and you get a bunch. So those are some options. It depends on what kind of game you're making. If you want it to happen a bunch or if you want to happen once only when you press down. We often will listen for this in process because process happens every frame and it's useful to check this every frame. And here's the challenge. Create a camera, listen for the WASD keys and move the camera based on them times some constant speed and delta. Now, you're going to need to use most of the things we've learned so far to do this. And there's one thing I'm going to do before that. I'm going to add some quick sprites to the scene so that it's clear that the camera's moving. Otherwise, you won't see anything. So I'm just going to drop in some characters. This guy. In the tree, you can mouse over something and press Control D to duplicate it. So I'm just going to make a couple little aliens so we can see the camera move. So this is your challenge. It's sort of like a camera that you might have in a map kind of game, an RTS, a turn-based strategy game, whatever, any game where you get to pan over a map. So it's camera panning. And just some quick hints before we move on. Some things to remember. Nodes, adding children to trees, vectors, how process works, etc. All right, good luck. And I am going to do this in just a sec. So get as far as you can. If something isn't working and you get frustrated, you can watch what I do in just a sec. Okay, cool. So we want to do this. So first of all, we want to create the camera only once. So we're going to do that in ready. I'm going to create a new variable outside camera2D. Then in ready at the bottom here, I'm going to do camera2D or camera equals camera2D new. And what do we do here? Well, I think that's okay. We don't need to position it here because we're going to position it with our keyboard. Let's go into process to handle this. I'm going to comment this out. Actually, no, I'm not going to. We're just not going to press space. And we're going to think here, well, what do we have here? We're going to need to listen for some inputs. We're going to have to listen to 4 of them, but let's just start with 1. Input is action pressed, because we probably want this to be continuous input. And we want we'll have to make a new action for this, right? So we'll go to project settings. We'll create a new action, camera down, add. We're going to add a key for it. It's going to be S, close. And then we put the name camera down here. And then what do we want to do? Well, let's pass for now. So if you remember how to move something down, what we have to do is add something to its position, and that thing can be a vector2 down. So we'll do camera.position plus equals vector2 dot down, and then we're going to want to multiply it by delta so it stays smooth, and then we're going to multiply it by some sort of camera speed. So let's make a constant for that. Our camera speed int or float. We'll make it 100 for now, camera speed. And this is something you probably need to tinker with to make something that you think is fun. And we usually do constants with scary, big, angry capital letters. So I'm going to fix that. Okay, let's try this out. I'm just going to try it with down, and then we can add the other ones if we want. So, okay, that's not working. What do we do when something isn't working? Let's try putting a debugger here in process. So while the game's running and you put a debugger in, it will hit that. So we'll see if we get this. We hit and press S. Now we hit this. That's interesting, but it's not doing anything. Let's have a look at what we'll call var position delta equal this. And then we're going to see what that is in the debugger. Press down. Position delta equals, okay, that looks right. 0.0, 1.66. And I realized that I've done something very dumb, which I forget all the time, is we need to add child camera, or else nothing's going to happen here. And there we go. So again, don't be like me. Remember to add child, or else nothing's going to happen. Your camera will not work. Anyways, we can remove this line because it's not doing anything. We have this camera position thing. Now we can repeat this with other values here. So if we add an up, vector2, and then if we add a right, vector2 dot right, and if we add a left, and we're going to actually improve this in a little bit, this will work. Let's go to project settings and add these new controls. Camera up is going to be S, or W is going to be A, and camera right is going to be D. Let's give this a quick play and see if we can move our camera around. Yep. Camera speed seems really slow though. And I want to show you another quick thing that is sort of outside of code, but useful, and that's export. So we've got this camera speed and it's a constant. Oh, it was a constant. If we want to make it something we can modify outside of code, let's just call it camera speed again, because this really isn't going to be a constant. To make it something we can handle outside code, we can do an export variable. What this does is, now when we select advanced control in our scene, we now have a camera speed variable here that we can change with this little box. So I make it 267, camera's faster, 473, camera's even faster. So this can be really useful if you want to expose properties for designers who aren't going to use code, and yeah, or even for yourself. You can make it 0 and the camera won't move at all. Let's think a little bit about this. This seems really like we're setting the position 4 times. That's kind of nasty, right? So another thing you could do that I think improves this is we can do var position delta is a vector2, and then we can do position delta plus equals, and then we can just add the position delta at the end. I kind of like that better. It doesn't like me there because it's not initialized yet, so let's do vector2 0 0. You'll notice that I'm not doing else here or elifs. That's because we'd like people to be able to press all of these buttons at once if they want to. You'll notice if we press up and down at the same time, nothing's going to happen. So think about that. If we make an else or an elif with the camera up, that's not allowed, but we'll always go down over up. So we'll press that. If we press both at once, we'll always go down, right? Because it's true for camera down. It doesn't even check this. So that's a design choice for you. Yeah, you can do that too. Cool. Okay, so that's all fine and good. We can move a camera around a scene, and that's almost something that might happen in a game, right? Let's do one last part of this section. We're going to talk about time. We've talked about space. Let's now handle time. So we talked about integers as like discrete units of numbers, numerical units. Games can also have discrete time, and that could be things like turns or like ticks. In really old games, you'd often move by ticks. You wouldn't move continuously. And we're going to make a game that uses a tick functionality like that. So what I want to do is have a function that runs at some fixed interval, and that fixed interval is going to be slower than process, so I can't just do it in process. But to do that, we need a way to time things outside of process. What I'm going to show you is the timer. So we can add a simple timer here, and timers interact with Godot's signal system, which we haven't covered at all, and I'm not going to cover until a future video, but we will show a very simple example of that here. So we'll do var timer equals timer.new. Timer is another kind of node, so we do have to add child. It goes onto the scene. Then we can give it some properties here. Timer dot, I think it's called wait time. We can give it a second value. We'll give it 1 second for this example. And then we will do timer dot timeout. This is a signal, and signals are kind of a complicated idea in Godot that we're not going to cover in depth here. But what we want to do really is just make it so a function is run every time this timer gets to 1 second. So to do that, we do connect, and then we want to give it, for now, the name of a function. So we'll call it handle timeout. And we have to make the function handle timeout. And then here we can just print timeout. Then the last thing you want to do is timer.start. And I believe this will repeat by default. So if we press play, it should give us timeout every second. There we go. Timeout, timeout, timeout. If we want it to only happen once, we can do timer.repeat. No, if you control click on something, it will give you documentation about it. so we can see what the properties it has is. One shot, I believe, is what we want. So let's go back to our code. Timer.oneShot equals true. And so this should only happen once. I'm going to put it before start. And if we press F5 to play, it'll say timeout once after a second. Perfect. Here's your challenge. I want you to create a timer. Listen for a press of the, I don't know, G button or the G key on the keyboard. When the G key is pressed, wait for 5 seconds, then print, you pressed G 5 seconds ago. You utter fool. Cool. Give that a crack. You have everything you need to solve this within this file, I think. So you should be able to handle it. Good luck. Okay, so this is how I would do that. The first gotcha, though, is that this timer probably has to live outside of our ready function because it has to be, we have to interact with it from process also. So let's create it at the top level here in our class. So we'll do var g timers, a timer, and then let's create it. Well, we have two options, actually. We can create it in ready, which means it will only be created once. We could also create it in process, which means we can create it every time we press G. That wasn't really specified here. So let's try it in process because that's kind of fun. There's good reasons why you wouldn't want to do it this way. So we'll do if input.isAction press G key. Let's make a input for that. G key. It's going to be G. Okay, so we got this. We want to do G timer dot. Well, we can configure it here if we want. Well, if we're doing it in process, we actually don't need it up here at all. So let's remove this one. And down here, we can do var timer equals timer.new. We can reuse the name timer because this variable is not in the same function as the other one in ready. We do wait time equals 5 seconds. We can do timer dot. This is the hard one. Well, first let's add child because if we forget this, nothing will work. We'll do timer dot timeout dot connect, and then we want to say print. We need to make a function called print thing, and it will say print whatever dumb stuff I set up here. And then we want to do timer dot start. Now, because this is in process, this will happen every time we press G. So we'll see if we can make a bunch of them happen. G, G, G. Well, 5 seconds pass and these all come up. Press it again, comes up again. And if we look at the remote here, every time we press it, you'll see we add a new timer to our tree. Now this is not ideal because we're not cleaning them up. So as a little bonus, maybe let's figure out a way to clean these up after we trigger them. The way to clean it up will be to queue free from within print thing, I guess. So I'm going to do something that you do not have to understand here, but we're going to pass in the timer to print thing. So print thing, and then we're going to print thing with the timer, and then we want to do timer.queueFree. We talked about queueFree before. It will remove it from the tree and delete the node. Don't worry about this too much. Really, this is making a little inline function, and we're allowed to pass in a variable that's going to be picked up here. It's called a lambda. Let's run this G, and we'll have a look at remote here. We'll see that as soon as each one is called, it resolves and it removes itself. So that works just fine. This one is the one we added up in ready. Okay, all right, don't worry too much about this one, but the other stuff I think you should know about for now. And yeah, that is the last section of just learning. We're going to do some challenges and then we're going to make a game. All right, thanks for sticking around so long. If you've gotten this far, first of all, damn, good job. That was a lot of content and also pretty dense. Second, you might be thinking, how am I going to remember all of this? My brain, it is so small and it's as smooth as a pebble, washed for 20,000 years in a great river. And I want to say to you, don't be so hard on yourself. Nobody remembers all of this stuff. We always look up documentation and search things on Google and whatever to remind ourselves. I am going to link a little cheat sheet in the description that you can download from my Patreon for free, and you can follow or whatever, but don't worry about signing up to give me money unless you're disgustingly rich and want like ad-free videos. If I did make a bunch of money doing this, I'd probably do something irresponsible, like buy an exotic pet or try to license the Whitney Houston cover of I'm Every Woman to use as the Hovering Skull theme song. Anyways, please take a deep, deep breath, subscribe to the channel, and we're going to do a few more challenges before we start on something bigger. Maybe a whole ass game, perhaps. All right, let's do a few more challenges to work on our intuition on how to use these different patterns we have been playing with. And then we can move on to make a game. So each of these challenges, I have 3 for you. They're a little bit bigger than the other ones sometimes. And you can solve them with knowledge from earlier in this video and use the cheat sheet that I have linked somewhere. When you see a challenge here, maybe think first about how you can break it down into the concepts that we have already covered here, and then start trying to fit them together. If things are difficult, just try to get as far as you can. Try to get to a point where you have some code and maybe a error message or something, and then see how I do it. The point is you want to try, you want to either succeed or fail, but you want to not give up, I think. And that will help you remember and develop your programming skills. Cool. First challenge. For each of these, I'm going to make a new scene. I'm going to make a folder called challenge scenes. I'll just call it challenges. And I'm going to add a new scene here. This is going to be called character movement. And we'll get started by opening our scene as usual, setting it to our main scene, and then adding a script. Okay, cool. Here's your challenge. I want you to spawn a Sprite2D on screen with whatever image you want. I don't really care. That's up to you, up to your creativity. Want that Sprite2D to be controllable by WASD keys, your WASD keys. Move them around. Move it around the screen. This is pretty similar to something we've done already, so I don't think this is going to be impossible for you. I'm going to give you a second to do this, and then we'll come back and solve it for you. Okay, I hope you had some success. Let's do this. So as usual, let's start with a ready function here. I think we're going to set up our sprite in ready, and then we can use process to move it around. So func ready void. I think I want to have a sprite that is outside of our functions so that we can set it up in ready and then access it in process. So we'll say var character sprite2d equals, well, let's just leave that there. And then we can in ready say character equals sprite2d dot new. We can preload. I'll show you another way to do loading in stuff. The preload's fine also. We used export before for a numerical value, but in this case, we can just drag in a texture. So we'll do var character sprite, character texture, texture2d. You'll notice that we already have a character texture option now in the inspector on the right here. Let's find a guy we like in import, tiles, character. I'll make a little yellow alien this time. Oh, he's cute. Okay. Spectacular. So now we have made this character. We want to do character dot texture equals character. And then what? Well, we can do, let's give him a position. We'll put him in the middle of the screen. I didn't specify this, but I don't know, why not? Character position equals vector 2. I'll do 500 for now. One thing we cannot forget to do is add child character. Now, this should place our character in the middle of the screen. I'm going to play this to make sure it is. Yeah, there he is. Not really the middle. I'm going to make the Y value a little bit less. That's close enough. Lovely. There are ways to get the exact dimensions of the screen, but I don't want to confuse you with that right now. This is fine. Okay, cool. We now have a character in the middle of the screen, but he's not doing anything. So let's do that. Do you remember how to use process to pull inputs? So we'll make a process function. Process has to have delta, and we will use that. And let's have a look here. We can go to project settings and input map. I already have camera down, up, left, and right here, but I can redefine things with the same keys if I want. So we'll just do, say, character. Add character down, add character left, character right, and we can give these WASD, WSA, and a D. Okay, terrific. Okay, now we can check for that. So we'll do input dot is action pressed. I think we want to get this input continuously, right? So let's do is action pressed. And then we want the string name. It is going to be character. It helps you out here with the autocomplete. That's handy. So character up. And then for this, we want to, I think I want to do something similar to what I did in the camera video where I keep a delta of these and then add that at the end. So we'll do var movement delta, and it's going to be a vector 2. We're not going to do this discretely also. It'll just be like in floats equals vector 2 dot 0. So if this pressed, we're going to say movement delta plus equals vector 2 up this delta, and we want some sort of speed. So let's make a new export for speed. Speed is a float, and we will. Now, the export's not going to show up when the script's not compiling, and it's not compiling because it doesn't see character speed here. So let's do that. Great. We now have character speed. I'm going to make it, I don't know, 100. And let's see. We just need to say character dot position plus equals movement delta. Okay, let's play this and see if we can go up. We can. Okay, terrific. Let's do the other ones. If you want to take a pause now, if you had trouble doing this and just want to finish the other 3, go ahead. It's just copy and pasting and changing a few letters, but it'll help you remember. But I'm just going to do that now quickly. I'll just copy it 4 times, and we'll do down, right, and left, down. It's easy as pie. Okay, let's see how that looks. Okay, we can move a guy around. It's practically a game. This is like lovely. We're good. And if we want to make him a little faster, we can just crank up the speed to, I don't know, 500. Ooh, okay, now it's a game. We can do this all day. Okay, cool. That's that for that challenge. I hope that kind of made sense. And yep, let's move on. Okay, this is your next challenge. So let's make a new scene for it. I'll call it coin flip. This one's going to be a little harder and it will require a little more kind of data management. And we'll open coin flip. We will set it as our main scene, and we will add our new script to it. Perfect. Here we are. So we're going to make a challenge. What is coin flip? We're making a coin flip game. The player starts with $1, one money, one peso, krona, euro, whatever you like. But they start with one of them. And the computer generates, well, actually, we'll say the player can choose heads or tails. And those will be by pressing H or T on the keyboard. Then the computer flips a coin. And by that, I don't mean don't physically simulate a coin flip, just simulate a 50% chance. So like calculates a 50% chance. And if the flip matches the player's guess, we double the player's money. And if it does not, we set the player back at $1 again. This is in Canadian money. So yeah, cool. Okay, here we are. Let's flip some coins. So a few things here. So we know the player starts with $1. So let's give ourselves a variable with that. So we'll say player money. It's going to be an integer and it's going to equal 1. Great. The player can choose heads or tails. So this is a player choice that is in input. So let's put that in process or func process. And we're going to want to track what the player choice is, right? So let's go to project settings. Let's add our new actions, choose heads and choose tails. We are going to do a plus here, and heads is an H and tails will be a T. Okay, our input map is getting pretty messy. So, I mean, we're not making just one game here. We're making a million little ones. So that's okay. Anyways, so what do we want to do? Let's first make sure that we can check the player's guess right now. So we'll do, let's see. So if input dot get action, what's it called? Get input dot. Why am I forgetting how to? Oh, it's is, right? Is action just pressed, and we want to choose heads. Well, let's make ourselves a variable for player choice now too. And player choice, this is going to be a bit of a weird one because there's really three values it can have, and that's heads, tails, or they haven't decided yet. So I am going to represent it as a integer also, and then I'll show you a bit later how we can make that a bit clearer with something called an enum. But we'll do int equals 0. And then I'm going to put a note up here saying player choice 0 equals not decided, 1 equals heads, 2 equals tails. We could also store this as a string. If you did it as a string, that's totally fine. Player choice equals 1. And then we do elif input dot is action just pressed, choose tails, player choice equals 2. Okay, so process is mad because we're not using, we don't have a delta in it. We have to delta limit. There you go. And we also need to underscore because we're not going to use delta for this game. Okay, now we are selecting our choice here. What's the other thing that has to happen here? Well, we need to flip the coin. So let's make a new function for coin flip. We'll do resolve coin flip void. Will it be a void? Yeah, I think it'll be a void because we'll do all the logic for it in here. So we'll do var flip equals randf greater than 0.5. We can also do less than 0.5. It really doesn't matter because 0.5 is in the exact middle. So whatever side it's going to be on is going to be a 50% chance. So greater than, less than, equal than, greater than, it's all the same. So flip is going to be what? A true or a false? We'll make it actually flip is heads. So there's a 50% chance the flip is heads. Flip is heads. Let's print. Flip is heads. Else. Print. Flip is tails. Next thing I want to do, I want to go back up here and just mention our choice. So print player chose heads. Print player chose tails. Then let's call our flip. Okay, cool. So here we are. We're in here. We've resolved. Coin flip is flipping. Let's see what happens when we play. It is screaming at me because it's resolving the coin flip no matter what. So I'm going to just do if player choice not equals 0, because if it's 0, the player hasn't decided yet. So we'll just do that. Play. Okay, so I press T and it does that because we're not setting it back. So I think we need to, at the end of resolve coin flip, do player choice equals 0 again. Shocked. Player choice is 0. Let's play again. Press T. Player chose tails, flip is tails. Player chose tails, flip. Is it always tails? Flip is heads. Yeah, okay. So it does change. Okay, cool. Now let's deal with the money aspect of this. So if flip is heads, we'll say flip is heads, and we'll do if, yeah. So we'll do if player choice equals, and we'll remember what heads meant. I swear there's a better way to do this too. 1, we'll do player dot money. Or so player money, we do times equals 2. Else player money equals 1. And then we can do the same stuff here. This looks like something we need to put in a function somewhere else, but we can talk about that later. Okay, and then I think we should print player money at the end here. We'll print current money, $, and concatenate it. And we need to turn this into a string if we're doing concatenation. Okay, I'm going to press play. I'll press T, so we fail, we succeed, fail, succeed. It's kind of fun. It's like gambling. We need a button that like makes them leave, right? Like walk away with their winnings at the casino. Pretty addictive. So this is functioning now. We can put some text here. We'll say you win, you lose. And again, this is all just UI essentially now. We can decide how to tell this story, and you may have chosen to do this in a very different way. Totally okay. So T, you lose. Okay, that's looking good. Now this looks pretty gross. I want to abstract this into a function, so let's do that. So do fuck handle win and the handle outcome, and then the outcome will include the flip his head. Yeah, sorry, it'll include the flip, which is an integer. Yeah, and then what we want to do is all of this in here, except I don't want to put the text. Okay, equals flip, and then we just do handle outcome 2 for this one, and then handle outcome 1 for this one. Okay, let's play this and see what happens. So it would be lose, win, lose, win, lose, lose, win, 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 lose. Okay, that feels like gambling. Okay, I think one thing I just want to show you here is a way to improve this. This is totally fine for this lesson, but we can also do something called an enum, which essentially lets us label numbers and use them in code. And I'll show you what that looks like. I'll say this is our or sorry, enum lip state, or coin state, we'll call it for now. There's probably a better way to call it, and it should be in camel case, or Pascal case, this is called. And then the values are going to be in screaming snake case. So undecided, comma, heads, comma, tails. Now we can do things like, well, first of all, we can use this as a type now. So player choice can now be a coin state, and it will equal coin state dot undecided. Now we get some warnings, but not errors, because these 1 and 2 actually translate directly into the 1 and the 2 here, and this is a 0. So we can make player choice though be coin state dot heads and player choice coin state dot tails, and then down here we can do player choice equals coin state dot undecided. Then in handle outcome we can also have coin state dot heads and coin state dot tails. This does a few things. I'm going to make this a coin state. This does a few things. One, it makes sure you only use valid values for this, even though these do actually equal 0, 1, and 2. If you tried to put a 3 in here, it would fail you, and that's a good thing, because also we can use these labels. It's much clearer that undecided is 0, 1, like heads makes more sense than 1, and tails makes more sense than 2. And then we want actually this to be states dot undecided too. Much better code, much easier to read. Yeah, I think this works just fine. This is a game, barely. I mean, it's got more interaction and it's less of gambling than most mobile games now. Anyways, yeah, so I hope that makes some sense to you. Yeah, nothing here should be too new. I used a times equals, but if you did equals player money times 2, that's exactly the same thing as that. All right, let's move on. Well, let's do one last challenge before we get into the actual game making. Making a new scene. This is going to be called Random Sprites. Random Sprites. We will open it, set as main scene. We will give it a script, create. Here we are. Okay, what's Random Sprites? Challenge. We want to, every 2 seconds, create 3 sprites in 3 random places, a 300 by 200 area. Whenever you create new sprites, delete any old ones. How do we do this? Okay, so the things to remember here: scene management, queue free, remember timers, remember randomness. Think about that and give this a crack, and let's go. Well, let's start in a ready function here, I think, because this is something we're probably going to set up as a timer, and then just have that timer run a bunch. Let's make a timer. So if our timer equals timer.new. Timer, remember, timer's a node. It needs to be on the scene tree. Timer dot, well, what's the, we know we want 2 seconds. So let's do timer dot, it's called wait time equals 2.0 time. Wait time. Yeah, okay. And then we want what? Well, we need to do timer dot timeout. This is the weird one where we have to pass in a function name so that we can do something over and over again. So let's make a function for that. We'll call that func, what's it? I guess generate sprites. It will be void, and we'll just pass it for now. We'll do timer timeout generate sprites. And to make sure this is working, let's just put a print statement in here, and we'll say generating. This is red because I forgot to put connect, and I forget this all the time. You have to do timeout.connect, and that connects this signal. Don't worry about it too much. I have a big video on signals you can look up if you want, and then we connect it to this thing. So let's just play the scene and see if we get generating every 2 seconds. We don't, because we forgot to do timer.start, of course. We generating. Okay, we love it. Good. All right, so now let's start making some sprites. So remember, there's 2 parts to this. 1, we have to wipe all the old sprites, and then 2, we have to make the new sprites. I think I'm actually going to make 2 functions for this. Call it clear sprite, generate sprites, and then I'm going to have a function called func like on timer tick, and it's going to do generate sprites. And we'll clear sprites first. How about generate sprites? And then we need to change the timeout method to on timer tick, and this should be good. Okay, so we can't really test clear until we actually finish with generate. So let's start on generate. what do we have to do? So it looks like we've got a 300 by 200 area on the screen. So in order to keep track of that, let's give ourselves a var for screen size. Actually, this can be a const. Const screen size is a vector2, and it will be 300. I always write this wrong. Equals vector2, 300 by 200. Terrific. So now we can use this x and this y in our random generator to get like a ceiling on it. Cool. So let's also, I'm going to add another at export var right texture. It's a texture 2D. This is the texture we'll use for our sprites so that we can actually see them. And I'll just choose a, I don't know, one of these. I can't quite see what this is. It looks like a little bomb or a little guy with a spike hat. Maybe a bullet. I don't know. Doesn't matter. Brilliant. So what do? We know how to make sprites. We'll go var. Well, we need to make 3, right? So we could just write all the text 3 times. Let's write it once first, and then we can think of a way to save some time. So var sprite, sprite2d, sprite2d.new, sprite.texture equals, well, we've got sprite texture. We do add child sprite. Let's see. I'm going to just play the scene and we'll see it in the corner probably. Yeah, there it goes in the top left corner. So next thing we need to do is generate a random location for it between 0 and 300 and 0 and 200. So let's do that. We'll do sprite.position. And if you remember, we have the randf range functions to choose a random point between 2 floats. So let's do that. We'll do vector2 and we'll do randf range. For the x component of the position, we can do between 0 and we can do screen size.x. And then for the y component, I'm just going to do a comma and a backslash, the backslash here too. Do randf range 0 screen size y. Yeah, okay. So this should position it at a random place. Let's try that. There we go. There we go. Oh God, there's too many of them. All right. We need 3 of these though, right? So do we know how to do something 3 times? Yeah, it's a for loop. So we'll do for, and we can do I or index int in, well, range 0 and 3. Remember, range is exclusive. It does not get to 3, so we'll do 0, 1, 2. Index is never going to get used, so I'm giving it a underscore so Godot doesn't get mad at us. And let's play, and we should get 3 after. Yeah, perfect. Oh God, there's so many of them. Oh dear. Okay, we better clean these up then. So time for clear sprites. One of the easiest ways to clear sprites would just be to do something like for child in get children. We do child dot queue for each. If you have other things as the child of your node, you'll have to do something else, but this will work for our use case. So let's see, 3 guys and nothing. Okay, what's going on here? Why aren't we getting any new guys? Let's see. I'm just gonna do print clear, do print gen, clear gen. It's only happening once. And why is that? Did we make timer one shot? Tick, clear, gen. Let's investigate this. Random sprites. Did you see that? Let's do that again. Okay, watch, it ticks. Oh, you have to look at remote to do that. Okay, remote, you see a timer? It ticks. The timer gets cleared because the timer is a child of this. So that's a really interesting gotcha that I didn't think of, but it's really good. Okay, so how do we handle that? There's 2 ways to do this, and I will show you both of them. The first one with the least amount of code is to just make a like a sub-child of random sprites to hold sprites, and I'll show you that. Just say var sprite container is a node2d, and then in ready we say sprite container equals node2d.new add child sprite container, and then we do. See, when we generate sprites, we do sprite container child sprite, and then when we clear sprites, we do sprite container dot get child. So now it should work. Yeah, good. I didn't expect that actually. I didn't think that that was going to be a problem, but this is the kind of thing that will always come up and you have to solve. Okay, and then another way you can do it is just actually keep track of these sprites as they are added. So I'm going to try that too. I'll leave sprite container because yeah, it doesn't really matter. we'll say var rendered sprites. That's going to be a array of sprite2d. And then we'll say up here in clear sprites, we'll say, we'll remove this code and we'll say for sprite2d in rendered sprites, sprite.queueFree. And then in generate sprites, we just need to make sure that we do this. We say sprites or rendered sprites equals a new list. And then we go, whenever we add a new sprite, we do rendered sprites dot append sprite. This way we don't actually have to get children at all, so it doesn't matter where they show up. They could be in their own container or they could be on screen. So let's just make sure this still works. Cool. Anyways, okay, that should work fine. I hope that is interesting and you learned something and you're ready to move on and graduate, if you will, to a more difficult kind of game. Hold on. Stop for a second. You've already learned a lot. Before we get to the meat of this video, or the dessert, whatever you like better, the I don't know, celebration of creativity, why don't you consider taking a little break, have a nap, go for a walk, speak to your loved ones. They miss you. Your brain needs a little time to absorb some of this stuff that you've learned, and then maybe come back, do a little review, and get ready to make a little game. All right. The nice thing about Snake is that it's what I'm going to call a primordial game. Primordial games are dead simple, but even implemented really simply, they're kind of fun already, with very little tech or bells and whistles or microtransactions or whatever. And you can build off that to make your own thing later. There's a reason why Snake was a hit in the 70s and came back in the 90s on those funny Nokia brick phones. And you'll see it's still kind of fun today. I mean, it's simple, but it's pretty fun. And we can theme our game however we want. I've chosen to make a kind of space rescue game because we have these cute little alien guys in the asset pack we downloaded. Feel free to change the theme. You could import your own graphics if you want. Just make sure that the size of them is going to match the tile size we set. That's all you need to do. So without any further ado, let me give you the spec that I'm working on here, and then we can start implementing it. So here is what I'm going to say. Venusian Rescue is a fast-paced retro arcade game inspired by Snake. You take on the role of an alien stranded on Venus, and your goal is to find as many crashed escape pods as possible. Every time you reach an escape pod, a new crewmate is rescued and will follow you around. This is the core loop. Player direction is set by the WASD keys, and the alien will continue to move in that direction until they receive a different order. When the player collides with an escape pod, it spawns an alien astronaut who will follow you loyally. Player loses if they collide with an edge or with a alien astronaut in their entourage. Movement is going to be discrete, with players and all astronauts moving one space per tick. And then quickly the art. The art is going to be in a simple pixel style, and we're not going to add any audio or UI yet. And we will be using assets from that Kenny Pixel Platformer pack. Feel free to get something else, just make sure that you're able to figure out the tile size and account for that. All right, let's actually make a thing. This is pretty exciting. If you want to actually just try to make the game based on the spec I just gave, like, go for it. See how far you can get. I think you have all the tools. However, if you are not quite ready for that, we're going to do this in a few steps. First, I'm going to try to break down the spec into different problems we can solve. And then we're going to work from there and actually start coding it out. So let's go. Okay, so I'm going to make a new folder here and we'll call it game. And in the game, we're going to create a new scene, call it game. And then we want to, of course, make it the main scene one last time. And then we are going to add a game.gd. Okay, here we are. We're in game.gd. This is it. I'm going to paste in the core loop that I set before, and then we can start working from this. This will take me a second. I just want to space it out so we can read it. Okay. So one of the core things you need to learn if you're going to be making video games is how to break down things that describe things kind of generally into things that are clear enough that you can just code them. And sometimes during that process, you actually ask and answer questions and make the design stronger and more clear. This is a pretty simple game though, so that might not come up too often. Anyways, let's start thinking about what is going to happen here. So we have input here. We know it's going to use the WASD keys, and the alien is going to continue to move in a direction until they receive a different order. So let's think about that first. So I think this is probably going to be something that happens. Well, this might happen in process because we need to accept input. However, it's a little confusing because we say down here that movement is discrete and all astronauts move one space per tick. Let's move that up here and think about that a bit. So this is kind of an issue because if movement is discrete and we move within process, we need to probably move the actual movement code out of process and put it in some sort of timer-based tick. So let's write that down. Actual movement, probably in a timer-based tick function. We've done this before. The other thing is that the movement is discrete in both time and space. So by that, I mean, they're going to move one tile at a time. They won't move like smoothly. So we're going to have to do something where we convert like tile coordinates to world coordinates and back. And a lot of this is because I might be getting a bit ahead of myself because I already know how to make this game. A lot of this is because we need to be able to compare tile coordinates to the coordinates of, like, for instance, a pickup. So that's down here. Let's split these out here. So let's see. So we need to figure out if our player is colliding with a pod. We can probably do that if we know the tile location of both the player and the pod. We can just compare them. Integer, or like vector integer to integer comparison is how I'm going to do that, I think. I just want to go into a little more detail quickly about what I mean by discrete movement and what we might have to do to get our grid to work properly. Have a look at this little guy. This is sort of like the guy we're going to use. And he is, at least in this example, 20 pixels big. In our game, I think he's 18. But if you look at the world here, you have a 4x4 world where you can be on any of these particular squares. And you'll see that when he's on this square, he's at position 0, 0, and he's at address 0, 0. But when he moves over, say 1 to the right, he's at address 1, 1, 0. And he is at position, and since each tile is 20 pixels, 20, 0. As it says right below him, x 20, y equals 0. And this is because, like, he is bigger than 1 pixel, so we just have to multiply or divide to get from one to the other, from position to what I'm going to call tile address. And we have the coordinates for tile addresses on the left and right here. And it is better to do it this way because it's much easier to compare if something is at a certain address, like 2, 1, versus checking if it is close enough to a certain vector float, which could be off by a little bit or whatever and give us some weird behavior. So again, when we have a discrete movement system like this, I prefer to work in these small coordinate values like this. We'll write something that will convert between these two so that we can work with it in our game. The hardest thing here is the following, which I'm going to do in a little bit, but let's do this first. So player loses if they collide with the edge of the map or an alien astronaut in their entourage. So edge of map, we can probably just test the position of the player versus like 0 or the screen size in both X and Y. Think about that. And then we need to also keep track of the position of every follower sprite also, because I think the followers are going to be represented by sprites also. So we'll say, here's the rescued queue members will follow you loyally. Now, this is kind of fun. I have a solution to this. It's a solution I had to try a few different things for, so it may not be what you come to. So if you can think of another way to do this, please do. We can keep crew members in an array of sprite 2Ds. When the player moves, when a pod is popped, we add a new crew member at the position the player used to be. And then we can do something like when the player moves, and this is what I think is quite clever. If you can solve this in a different way, that's also good, but I think this is kind of fun. We move the last crew member to be in the previous place of the player. So rather than move every single crew member, we just move the final element in the tail to be where the player used to be. And that makes it look like it's moving because we aren't animating anything. It's kind of a clever way to do it, and we can mess around with that array popping and appending logic for that. Okay, yeah, and then here we'll say, like, if we have a list of locations for crew members, we can check these and see if we have a collision. Okay, cool. There's another couple things that I want to add here that weren't really in the spec, and that's like we want to display a background that shows the legal playing area, because it will be really hard if you just have to guess if you're going to run out or not. That's not very fun. And there's another thing too. Again, these are the kinds of things maybe you have a conversation with your designer to tease out more requirements, but something like when a pod is picked up, we need to spawn a new one at a random place. So let's talk about this one. So since we're on a tile system, we probably just need to loop through tiles. Godot has a really cool tile map system that we're not going to use for this. We're just going to render sprites. Probably have to make the background tiles a lower Z index so they do not overwrite our little guys. Terrific. Okay, and then when the pod is picked up, we need to spawn a new one at a random place. This also happens at the beginning. So we've done this very recently, but generate a random legal position, put the pod there. Okay, cool. I think we've teased out a lot of the things we actually need for our game here, and we can start actually building it. So where do we start? I think I'll start with the background because we haven't really done this, and it could be kind of interesting, and it will expose a few more interesting quirks of our system here. So let's do this. We're in a tile system. Okay, cool. So let's first make a ready function here. We've done this at least 10 times by now. And let's make a function called setup background. We don't have one yet, so let's make one. So I'm going to put that down here by this. We'll go fuck setup background, and it returns void. Now, what do we need to do in here? Well, I think we need to go through some sort of loop and place a tile at every combination of X and Y in a grid. So let's do that. We're going to do 4. We'll do X in range. And what are we ranging over? Well, we need to decide on the size of our arena here. So let's do that. I'm going to go up here. I'm going to make a new export var. It'll be game size. We'll say world size. And that's going to be a vector2. We're using a vector2i because we're going to be dealing with this world in like integer coordinates that are going to be 1 tile each rather than vector2 coordinates that are going to be 1 pixel each. And you'll see why soon. Okay, cool. So now if we click on game here, we need to make sure this compiles. I'm going to pass this. Okay, we'll have a world size here. So I'm just going to make it, let's say 30 by 20 for now. We'll see how that looks. So for X in range, we will say world size.x, and then for Y in range, world size.y. And I think it will default to 0 too, but I'm just going to make this explicit, 0 to that. So we should go up to 30 and then up to 20. And this isn't gonna be that bad. We're going to actually spawn, 600 tiles here. When you see this kind of thing in code, you should be a little worried if it's in like a process function, because this is a lot of extra processing that can be hidden in this double loop. It'll happen 600 times though, 30 times 20. Okay. Cool. And then what do we do here? Well, let's make a new sprite. So we'll do var tile, and I'll call it bg tile equals sprite 2D, and it's going to equal sprite 2D dot new. Lovely. Okay. And then we'll do bg tile dot texture equals, well, what do we need? I think we need to make a background tile texture. I'll use export again. Preload is also fine if you'd rather do that. We'll do bg tile texture. It'll be a texture 2D, and we need to comment this out. Now we have this here, and what do? Let's go to imports and let's grab a background tile. I think I found one that's just kind of a dirt. Can find a nicer one. Hold up. Oh, those are backgrounds. Don't use the things from the backgrounds in the Kenny tiles because those are not 18 by 18, they're 24 by 24, and they won't match the other tile sizes. So I think we're gonna use a 122 is what I have written down here. There we go. And it's 18 by 18. We need to make sure all of the tiles are the same size or else things aren't gonna look right. Okay, so BG tile texture equals BG tile texture. And what do? Well, we have to add it as a child. Okay. And then what? We need to position it. So this is kind of the interesting part. So if we do bgtile.position equals vector2 x, y, that's going to be a problem because these tiles are 18 by 18, right? And if we position them by like 0, 1, 2, 3, 4, 5, they're all going to overlap. So let's have a quick look at what's happening. Yeah, they're just all clumped up in the top left of the screen there. Not great. So there's a few things we could do. We could just multiply by 18, and that works. I think this is kind of the outcome we want here. But we're going to end up having to do this a lot, right? Because all the time we're going to have to convert between these 0, 1, 2, 3, 4, 5, 6 coordinates and these 18, 36, whatever coordinates. Because we're going to do a lot of our math indexed on tiles, but we have to render things based on this 18 pixel size or whatever size you choose for your own art. So first of all, let's make this a constant. So we'll do const tile size equals 18. Every tile in the game is going to be 18 by 18. We'll use that here. And then I'm thinking I'm going to use this a few times. So I think I want to make a function that takes in a vector2i and gives us back a vector2 for a position. So let's do that quickly too. We'll call this v2i to, we'll call this tile address to position, and it takes in a address, which is a vector2i, and it gives back a vector2, which is the position that we want to place whatever tile is on the actual screen in pixels. And then all we have to do here is what? Well, return address times tile size. And then we can, instead of this, do tile address to position, and we do vector2i x, y. And that just makes it a bit clearer what's going on. Let's look up at our notes here. We probably want to give it a lower Z index because we're going to put things on top of it. So let's do that. We'll do bgtile.z index equals -1. Okay, I like that. I'm happy. Let's play this again to make sure it's working. And yeah, it looks okay. If you want a challenge, I might give this later, but it's really monotonous looking. And it might be nice to have it randomly choose a different tile occasionally that has a different arrangement of dots on it. But that's not necessarily part of this tutorial. Now, there is one thing that is coming to mind while we do this, and that's that the camera is way too zoomed out, and it would be nice if it was double zoomed in. So let's make ourselves a camera too. So we have set up background here. I'm going to make another little note for myself here. I want a camera that is probably 2x zoomed in to show off that sharp pixel art. So let's make a func setup camera void. What's it going to do? Well, we're going to make a camera. So we'll do our camera2D equals camera2D dot. What are we going to do? We want to add it as a child. Remember that if we do not add it as a child, it won't work at all. Let's see what happens when we do this now. Nothing. Okay, because we're not calling this setup. Let's see. So now we have add child camera. We can play and see what happens. Remember, it now offsets it weirdly. So there's a couple things we need to do. We need to center the camera and change its zoom level to, it's going to be a vector to 2. So if you want to try this yourself, please do. I'm going to move on with it in just a second here. So pause if you want and give it a crack. Okay. How do we center a camera? Well, let's think about this here. A camera has a position just like any other node. The center of our game is going to be at, well, probably 1/2 of our world size, right? But multiplied by our tile size. So let's try to do that. Do camera.position equals, let's see, world size times tile size divided by 2. And let's play to see if it centers. That looks centered to me. Terrific. Remember, we can take this vector2 world size This is going to divide it by, or multiply it by 18 and then divide it by 2, which will center on the 1510 tile. Let's change its zoom level. So we'll do camera.zoom equals, and we didn't cover zoom, but zoom just takes in a vector also. We can do vector 2.1 times 2. I'm going to play it. Look at that. That's like possibly a playable game surface. I'm so excited. All right. I'm gonna actually crank this back a little just to see, do we have, yeah, I think that 2 is too much because we don't see the top yet. There we go. Let's do this for now, 1.66. But you can tweak this yourself depending on what you want. You can even make it so the camera moves with the player later if you want. Okay, so we have a camera now. That's good. What do we want to do next here? Let's make a player come in. I think it's time for that. Let's do a setup player. So we'll do that here. Setup player. What is the player? I think the player is also going to be represented by a Sprite 2D. If this were a more complicated game, we would make a brand new data class and a brand new file to handle the player. But I've purposely kept all of the games in this video to be single files just so we can manage them all in one place. But you can make more files, and you almost always will for any game of any reasonable size. But for now, we're just going to use the built-in Sprite 2D to represent where the player is in the world. So let's make a variable. It's not going to be exported. It's going to keep track of the Sprite 2D that is the player in the world. And it's going to start as null, which is fine. And then in setup player, we'll do player equals Sprite 2D dot. We need to give the player a texture. So let's do that here. Player texture, and it's going to be a texture 2D. And now we can add that here. I'll find a little guy in my file system. I think this little green alien is just fine. In fact, better than fine. I think he's perfect. Player.texture equals player texture. All right, we need to place the player somewhere. Let's do player.position. Let's start them in the very center of the screen. So let's think about that. Well, the position has to be a vector 2 that is pixel coordinates, but I want to position everything based on these like world index tile coordinates. So let's do something like this. We need to, well, we already have tile address to position. So let's just use that, right? So we can do tile address to position. We'll do world size divided by 2. This is going to do integer division for us, which is fine because, you know, it'll be 1510. Even if it is off by half, that'll work too. He'll just be offset a little. So if we press play, nothing happens. Your next challenge is to figure out why that is. What have I forgotten to do here that I've forgotten to do a million times? Okay, I'll tell you, I'm just gonna make this float division. We can just click on this warning here to ignore integer division. You'll see this here. You click ignore. We want this integer division. It does warn you because it messes you up. That's not what I screwed up. What I screwed up is, of course, adding the child to our tree, or else this won't work at all. We press play, and it's still not there. And why is that? Let's inspect our remote game. Everything is a Sprite 2D. We have everything. If this. We don't have a player texture yet. Why is that? Game. Player texture is empty still. I messed that up. Let's just drag it in, save, play. We have a little guy. Okay, cool. That's the start. Okay, so we now have a player on the screen. What's our next move here? Okay, so player direction. Movement is discrete. So there's a lot of things we need to do here. Most of these are going to happen like over and over again throughout the game. So let's move this text down here. I think we need to figure out like a tick system here because we don't want to make the player move every single process. We want to make the player move every, I don't know, 0.3 seconds or something like that. So let's do that. Your next challenge then is to set something up so that some function called, we'll call it tick void print. Set something up so that tick is called every some number of seconds and make that some number of seconds something that we can set from an export variable. Okay, good luck. Okay, so I think you probably figured this out. We want to do a timer. So we'll do set up timer, and set up timer we can do up here. And all we have to do is, well, you remember this. We'll do, where should the timer live? I think the timer can live in this func because we're just going to be throwing it onto the game tree. So we'll do var timer equals timer.new. If in the future we need to pause it, we're going to have to probably put this variable outside, but I haven't decided if we want to pause yet, right? So var timer equals timer.new. We know how to set this up. Time equals what? Well, I promised that it would be an export variable, so we'll do that. So we'll export var tick speed, tick time. It sounds gross, but okay, float. And you can give these default values. I'm going to give it 0.3, and it will show up as 0.3 there. And then if we change it, it'll change, but not in code. It will take this value instead. I'm just going to press this to make it the default. Awesome. Okay, our wait time equals tick time dot. Well, what do we need here? We can do timeout dot connect equals handle tick, which is called tick. Excellent. And then timer dot start. Am I missing something here? Am I missing something here? Yes, I have to do agile, or else this won't work at all. Okay, let's see if tick works. Nope, we get an error. Yeah, this is important. You can't start until it is added to the tree. Tick, 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 tick. That's great. Okay, that looks like a good enough speed to test with. All right, what happens in tick? So players and astronauts move one space per tick. So let's figure that out here. So first of all, we'll ignore the astronauts for now, and we'll just do the player. So we'll do player dot position equals, well, what? We don't have a direction yet. So let's just imagine right now they are going up. No, let's go right. Right seems good. Okay. We'll just imagine they're going right. So we'll make a variable for direction here, which we're going to have to change later because we're going to be able to change the direction, but it will be vector 2i dot right. You remember that is a vector 2i that looks like, I think, the 1, 0. Player dot position equals player dot position plus vector 2 direction. Is kind of a problem, right? Because we're trying to add two different things. Player position is the pixel position of the player in the world, and direction is a vector 2i right. One thing we could do here, of course, is multiply by the, what's it called, tile size. And this should work. Let's play it and see. No. Oh, yeah. It doesn't work because we're trying to add a vector 2 and a vector 2i, and that doesn't work. So let's think of a cleverer way to do this. So one thing I would like to do is not deal with player position directly when I'm doing any logic. I want to turn it into our tile address, and then later I can set it back again. So let's figure that out. So we'll have a new variable called player address, and it's going to equal, well, we have a function to get from address to position, but we need one to get from position to address. So let's make that func position to tile address. And we will take in a position, which is a vector 2. It will return a vector 2i. And what do we do here? Well, we can return the position, and can we just divide it by tile size like that? Yeah, probably, because we want this to be a whole number and we're dividing by an integer. This should just make us a vector 2 integer, hopefully. We can find out at least. Player address equals, we can do position to tile address. And because the integer division is going to truncate it, that'll actually work more or less like rounding for us, and we won't have problems, hopefully. We'll see. Player dot position. Then we do player address plus equals direction, and then we do player position equals, and we'll do position or tile address to position, and we'll do player address. And this way, all of our logic, which isn't very exciting here, it'll get better, is done using our discrete tile coordinates, and then our rendering gets updated using our actual pixel coordinates. Let's see if that works. Hey, he's moving to the right. Oh no, he better stop or he'll go off the screen. Okay, cool. That's awesome. Let's get control over this guy. We want to use the WASD keys. Tick runs about 3 times a second. If you put an input check in here, there's a really good chance that it's not going to actually pick it up because you might not be actually just pressing a button at that time. So I think input functions still have to go into process. So let's make a func process. We want to give it a delta that we're not going to use, returns void. Now, what do we do here? Well, we know how to get input. Let's just start with getting input. We should pass this for now and add some inputs. Project settings. Actually have character left, character right, character down, character up already from a challenge. So maybe I'll just use these. Yeah, why not? Yeah. But you can go back in the video to see how to make those. And here we go. So we'll do if input dot is action. Do we want pressed or just pressed? I think we'll do just pressed. My thought here is that we store whatever the value is, and then until a different value is selected, we will keep it. So it doesn't matter if it's pressed or just pressed. But we'll do character up. And then here we're going to store a direction. And since we need to store it and use it on other functions, we need to store it at the class level. So we'll do direction, it's a vector2i, and it's going to, well, we need to give it a default here. So we can actually default to 0, and that's not moving. That seems fine. We could also start him moving by, or her, it, them, moving by giving it something, but whatever. Character up, we'll do direction equals vector2i. Now you'll see this is saying, hey, we're already using direction, and that's a good sign to remove that because we don't need that. And we will say, let's move character. Let's quickly copy this and paste it and add in all of the other directions. Left, down, right, left. Okay, we should be able to move the character now. So I'm going to press play. Okay. And if you press the button, he's just going to go off in whatever direction that is infinitely until he dies in the cold vacuum of space. Goodbye. Okay, cool. That's great. Okay, so we have movement that's discrete in both time and space, with players and astronauts moving one space per tick. Let's move this here where it is actually being implemented, and we'll move this here. And let's see, what else is here? Let's talk about killing our player. First, we'll just do it with the edge of the map, and then we can come back to it later when we have astronauts following us around. So let's do that. Where are we going to do it? Well, let's do it in our tick here, because this is when movement is calculated. And I think where we want to do it is after we know the player's new address, right? So I'm going to put it in here. We'll update the player's position at the very end of this. So update player renderer. And in here, we can do anything we want to do with the player address. So what do we want to do? We want to know if the player has gone off the screen. Off of the screen, sorry. We have to be clear here. I mean off of the brown area, off of the play zone. So how do we do that? Well, what information do we have? World size is definitely where we're at here. So why don't you do for me, think about how you could do that and see if you can figure out what kind of check we can do here to see if the player should die. I'm going to make a quick function here called die, which we'll fill out later. And we'll just print, oh no, I am slain. Okay, so you figure out, or at least try to figure out how we can use player address and our world size to figure out if the player has left the play area. And just remember what player address looks like. Let's actually debug this before we go into this. I'm going to put a debugger down here, and we're just going to see what every tick looks like. So tick 1, player address is at 1510. And if we press play here, he's not moving at all. There you go. 1610, he's moving right. 1710, 1810, 1910. I'm going to try to move him down here. 1912. Again, it goes up by 1 depending on what direction you're going in. Okay, try to figure out what it's going to look like if the player has left the play area and use that to call die. Okay, I'm going to do this. So couple things we need to know. For one, I'm going to remove this debugger. If the player is at y equals 0 or x equals 0, they're on the edge. So if it's less than that, that is a death. The other thing to check for is if it's more than the world size is x or the world size is y. I'm just going to quickly print player address here. That might be an easier way to track this. So you can see, clear what's going on there, I think. So let's do this. I'll say if player address dot x is less than 0, or player is less than 0, or player address dot x is greater than or equal to, I think we want it to be, what's it called? World size dot x, or player address is greater than or equal to world size dot y. This is a very nasty looking condition. So I'm just going to split it up by doing that, and that's a little easier to read, I think. And then down here, inside of the block, we can say, let's see if that works. I might be just of X invalid operand. Oh, it's here where I'm saying player address. It should be player address.y. Okay, let's see if we can kill this guy. Oh no, I'm slain. That looks right. And then if we go this way, oh no, I'm slain. Okay, and let's go up the top. Slain. Okay, good. And then one more. I should make this guy faster. This is ridiculous. Slain. Okay, perfect. All right, we now can die. It's a little freebie I'm going to give you for die. There's a few things we could do. We could just reset all of the variables manually, but the easiest thing to do is do get tree dot reload current scene, and this just reloads the current scene. Is what it says. I shouldn't have to explain that. So let's just see what it looks like when we die now. Let's watch this man die. Boom, back to the beginning. Awesome. Okay, that's working fine. We have invented death. Okay, cool. Let's have a look at our spec here. So players lose when they collide with the edge of the map. Let's just move this over up here. And I'm going to remove this print statement for now because we don't need it. What's next? Let's start spawning the pickups we want for the player to pick up so that they can generate their snake tail or their friends, their survivors that they're going to rescue. So how do we do that? I'm going to challenge you to do that. But first I'm going to make a function for it. We'll make a function called spawn pickup. And then we're going to put that somewhere down here. And down here, that's for you to do. So spawn a pickup. It's going to be represented by a Sprite2D probably. It should appear somewhere random within the confines of the game world. Okay, I'm going to let you do that. And then if you get stuck, you can just play. All right, let's do this. So we'll do var pickup equals, going to be a Sprite2D also. Again, I think in a more complicated game, we might have a special class we make for pickups that, has, its own special point value and it can do its own address math and stuff. But for now, we're just going to use Sprite2Ds to keep it simple equals Sprite2D. You've done this before. We can do, we're going to need to add a texture for this, right? So let's do an export var pickup texture 2D. And I think I wrote one down that I liked for this. Is tile 0023. Okay, 0023. Okay. So we select game. If it's not compiling, it should be fine. Okay, select game. And we want to add a pickup texture. I'm doing this little guy because it looks like a little treasure chest, I guess. Or maybe a space coffin. I don't know. That's where his friends are living. Pickup.texture equals texture. And then we'll do, we need to choose a random place to drop this. So let's do that. So var random location is going to be a vector2i. Again, we want to generate an address for this, not a position. And then it's going to equal vector2i. And then we can, in here, generate two numbers. So randi range 0 and world size x. And then randi range 0 and world size y. We're going to add child pickup. Why is it mad at me? It's mad at me because random location is not being used. And let's figure that one out. We'll do, it's because we're not actually using it. So pickup.position is going to equal what? Well, we have our address to position, and we'll do that. Remember, this will convert our tile address, which is like 0, 1, 2, 3, 4, to a pixel position on screen. Okay, let's play this and see what happens. Hey, that's a pickup to go to. I'm going to go for it. Okay, of course, we're not actually colliding with anything yet, so maybe that's the next thing to do. I have a debugger message here. Okay. I need to call this something other than position, so I'll call it pause. Okay, great. So let's just move this stuff to here, spawn pickup. Okay, we have a pickup now. How do we figure out if we have collided with the pickup? Well, that's probably also going to happen in our tick here because we have this player address and we also know where the pickup is. So how do we do that? We can probably do it after we check if the player has died because it doesn't really matter. There's never going to be a pickup spawned outside of the world. So yeah, we can do, we can check if player address and we can check if it equals the pickup address. And right now, I think our pickup lives in here only. So let's actually move our pickup variable out into the world here, and then we assign to it when we spawn the pickup. So we don't need to use a var. We just say pickup equals, and this will use the pickup variable that's on the class. Okay, cool. So if player address equals pickup, well, we don't have an address on it anymore. It just lives in the world with a position. So we're going to have to get the pickup position, and then we need to convert it to our coordinates. So we'll do, what is it? Position to tile address. And I'll put a colon, and it's still mad at me. Oh, yeah, it just wants something in this block. So then we will do what? We'll just print pickup, and then we can check if this works. Pickup. Okay, so it's working fine. What do we do when we pick up? So let's make a new function called do pickup, or pick up. Okay, that's a funny enough thing to write as a function. Let's do that. Pickup. It's going to be void. So the first thing I want to do is, well, we're going to have to spawn a new follower for our guy, but first let's just destroy the current pickup and make a new one. So we actually have that functionality already. We'll just do pickup.queueFree, and then we'll do spawn pickup. And that will just spawn a new one in a different place. Let's see if this works. Oh, okay. It's almost a game. I think to make this a game, it has to be faster though. So I'm going to crank up the speed a bit. Speed is going to be faster. There we go. Cool. Yeah, so that works. Now we need to have followers, or else we will feel like our life is empty. When I first started building this, my theme idea was it was going to be a cult where you're picking up like money and then people would start following you around. But I thought that was like a little bit like gauche and insensitive. So I decided to do like aliens. Anyways, let's do this. So what do we got here? What's left to do? So the major thing to do is the crew members following you. This is already done. So I'm just going to move it into setup background. Crew members following you is the hard part here. We have this done. I think we already have notes for it, and we'll deal with this in a sec. Okay, cool. When the player collides with an escape pod, we need to spawn an alien astronaut. That's what we do next. Okay, cool. So how do we do that? So I think we'll start with what we know how to do. We'll do a spawn follower. I think we need to spawn follower at a specific address because we can't just do it randomly. So we'll just do address vector 2i. And I'm not going to bother making this a challenge. We just want to make a follower appear here. I'm just going to write this out because we've done this a few times already. You'll be fine. So we'll do follow. So we'll do var follower equals sprite2d.new, and then we'll do follower.texture equals, well, we need a new texture. Let's make one. Texture 2D. I think I'll just make a different alien. That looks like someone I'd want to follow me around. That's for sure. Wonderful. So back to our spawn follower here. Do var follower equals sprite2d.follower texture equals follower texture. Well, we will make follower dot position equals address to position address, and then we'll do child follower. This should be fine. We'll do that here. Spawn follower. We need to put it before we free the pickup, though it's queue free, so it won't matter. And we get the address by taking the pickup dot position, and we do position to tile address pickup position to get the actual coordinates for it. Let's see if this works. It might not. I might have forgotten something. Nope, that works. We now have a follower. He just sits there, which is, I think, lazy personally, but we can work with that. How do we get these guys to start following me and preferably giving me money? Am I right? Okay, cool. Let's look at that next. So I'm just going to move this here, and I'm going to remove this stuff also because we've already done it. This stuff is also done, and I think the main thing left to do is deal with the followers following me. Okay, so I have a design for this. I've already kind of mentioned it, but this is something I want you to think about. How would you do this? Just guess based on the things we've done today, what you would put in place to make this work. And even if you can't figure out how to code it, just get some ideas and maybe be wrong, maybe be right, but learn from it. I'm going to show you my solution. There are other ways to do this, but take 10 minutes to try to figure this out yourself. If you can, I'm going to be kind of impressed, and I'll give you a psychic high five. Cool. Let me show you my solution to this. So followers have to always move when the player moves. The point of snake is that the tail is attached to the head, and that's the problem, right? So cool. We need to move our followers. So I think we have to do that in tick because that's where everything else moves. And we're going to move them first before we start checking for collisions. So let's do that here. Move followers. First off, we are going to have multiple followers and we need to keep track of them. And we're going to keep track of them in an array. So let's make a followers array up here. Our followers is an array of Sprite2D. And it's going to start as an empty array. And then whenever we create a follower, spawn follower, we do followers dot append follower. Cool. Now we have a list of all of our followers. What do we do now? Well, in tick, what do we do? Well, let's check if we have followers first. If we don't have any followers, there's no point in running this and it might cause problems. But if we do have followers, we will do this. Followers dot pop front. This takes the first element of followers off and puts it into this variable. Then what we do is do follower to move dot position, and we want this position to be the player's address before it moved. So to do that, we actually have to keep track of the player's old address. So we'll do var old address vector2i equals player. I'm going to check. I'm going to use old address in here. We actually have to make it a tile address to position of this so that we can make sure it actually works properly. Yeah. The next thing to do is to put the follower back onto the array. So followers dot append. A bit about how this works. If we have one follower in our array, we grab it out and the array is empty. We move it and we put it back in. Doesn't matter. It's totally the same. But if we have, say, 3 followers, we grab the first one in the array, which is going to be the last one on screen, the furthest one away from you. We move it to be the closest, and then we put it back at the end of the array so it doesn't move until we've gone through every other element. This way we're not actually moving all of the sprites on screen. We're just moving the last one to be right behind the player. And it's a pretty clever way to keep them moving. Let's see if this actually works though. Hey, look, I've got a little guy following me. Okay, this actually makes it way funner. And I see a bug. I see that it looks like that our pod can spawn off screen. So that's something to fix really quick. I'm going to bet that's in our spawn pickup code. And we remember that randi range actually is inclusive. So we need to do -1 for those. And that will fix that. Okay, cool. So we have followers following us, which is great. The next thing to do is to make it so if we touch one of our followers, we die. And that's a little simpler. We're kind of going to brute force it. There's smarter ways to do this, but I don't really think it's appropriate to get into them right now. But we shouldn't be able to do this, right? And there is one little quirk of it that we're going to have to work out with input after, but we're almost done. So what do we do here? Okay. And I think the way to do this is before we move our followers, we check if we are colliding with one. So we'll do, let's see here. How we're going to check if we're colliding with one. Why don't you do that for me? Eventually, at some point, we're going to call die, right? That is the only inevitability in life, that at some point we die. But how we get there is up to us. So let's figure that out. If you have had a chance to try this out, that's great. The kind of brute force solution to this is to do it this way. We'll do for follower in follower. We can get their tile address. So we'll do our address equals follower dot position, and we will wrap this in a tile address, or sorry, position to tile address thing. This is a vector2i. And then if we do if address equals player address, you die. And let's see how that works. Now there's a really easy way to test this out. I'll show you in a sec, but oh, I accidentally did it. If you have at least one follower and then you just press backwards, it looks like you die. We should fix that because I think in Snake, you aren't allowed to input the exact reverse direction that you're going in. I'm just going to try to get a legitimate death here. And like, I don't know, it's already a little bit fun with these guys following me around. I need one more. Okay, let's see if I can die now. Yeah. Okay, that's fine. Cool. Yeah, so it looks like we can now collide with a follower and die. So one little fix here. Notice that it's really annoying that when you're playing and you have one follower and you're going right and you just press left, you instantly die. We don't want that to be allowed. So we want to actually do a check in here, probably to not let people choose the opposite direction. So why don't you try to solve that? Okay, I'm just going to do this. Direction not equals vector 2i down, and we'll just copy and paste this a few times and make sure that it is the correct opposite. And this should prevent that kind of annoying thing. Oh, it's called direction, not current direction, sorry. My notes said current direction. Okay, and you might want to put this on a different line if you want. I'm using really big text because people in my YouTube comments get mad at me if I do not do that for them. And I accept that. Accessibility is really important. And just remember, I don't think you can put if you put a space after that, they get mad. So be careful about that. No spaces. Yeah, I'm going to play this and see if I can. Yeah, so it makes it kind of interesting immediately because you can't turn on a dime when there's nobody, but it also protects you from dying. I'm pressing down now. So that makes it a little better. Okay, let's have a last look at our spec here and see if there's anything else we need to do. Yeah, you can still kind of do a up, left, down to die instantly, but you have to do that on purpose. Okay, we set up our background, our camera, our player, our timer. We spawn a pickup. The rest of the logic is kind of in our timer here. So that's in our tick. We move our player. We check if they are off the world. We check if they're colliding with a follower. We move all of their followers. We pick up something, and then we move them on the world. We change their sprite location. And other than that, everything just kind of comes off of these functions. So that's okay. There's a lot of cleanup we could still do. I think while I do that, I want to put all the setup functions together. And this game is just big enough that I think it should probably be in multiple files, but I'm not going to do that. I'm going to put the setup stuff at the bottom here. I'm going to put these, utility functions. I'm just going to put some headers for these things. Yeah, I'm going to remove this. And then we have pickup. These are all kind of logic that happens based on tick. So I'm going to move process up by ready, tick right underneath that. And you can see the structure on the left here. We have ready, process, tick, die, spawn pickup, pickup, spawn follower, set up background, set up camera, set up timer, set up player, tile address to position, position to tile address. And it says we're at 157 lines of code here. Hopefully 157 lines of code that you now understand. But if we remove all the comments and spaces, we're going to be at about 100. And that's kind of what I promised you. I think that this is a functional snake game, or as I have called it, Venusian rescue. So take a breath, and then I want to give you a few more challenges to leave you with to make this game your own. So yeah, good job. If you got this far, I know a few things in this are a little bit hard to wrap your brain around, but hopefully you kind of see how this kind of thing gets made. I'm going to give you some challenges, and then I'm going to show you how to build and release this. Okay, please stick around a bit so I can show you how to actually build and release this game. But for now, I want to give you some future challenges that you should work on yourself to make this a little bit less crap. So first one, try to change the theme, the quote unquote story and the sprites to your own. You can use the ones in the Kenny tiles that I showed you, or you can just make your own. I will show you how to do that another time maybe. We can change some of our variables. How does a bigger arena look? How does faster movement look? If we have a bigger arena, maybe we make the camera follow our snake and we create a huge open world, massively multiplayer snake game. Don't do that part, but you could do like the big open world kind of thing. That would be kind of neat. 3, you can add some random variants to the arena ground to make it look less monotonous. If there are 3 or 4 similar tiles with different like noise on them, they'll look a lot nicer. 4, what if we wanted to make this game a little more like difficult? What if we wanted the tick speed to get faster over time? That might be interesting. 5, what if we wanted to add some randomly placed static obstacles to get in our way and make things a little harder too? 6, what if we wanted to make it so the walls didn't kill our snake, but instead warped them to the other side? It sounds complicated, but actually it isn't that bad with what we've got. 6, what if we wanted a win condition when the snake gets to be a certain length? We haven't covered any UI or anything, so we can't really show anything like that unless you get a little bit creative. But you could have it print to console, or I don't know, crash the game or something when you win. And finally, get creative, add a new feature, do something crazy, make it cool and your own, and share it with me once you have it up or have a screenshot or a video of it. And if it's cool, I'll show it off. So I'm not going to do these challenges in this video. I might follow up with how I would do these things another time. So subscribe or whatever. And again, yeah, send in what you make. I'm curious. I want to know how you approached this. I want to see your creativity on display. Okay, so if we want to package this up for release, we can go to Project, Export, and you'll probably see something like this. You'll see presets and it'll be empty and you'll have to click on Add. And let's add a web one and a Windows desktop one. You can add whatever you want. And then what you want to do is you'll see no export template found at expected path, probably. Click on Manage Export Templates and you want to make sure you find the ones you need. So we'll do web and we'll do Windows. And then if we close this, or if we click Install Selected Templates, it should take a few minutes to get those onto your computer, as long as you're connected to the internet. Okay, and they'll show up as they install right down here. Okay, click on Close once they are done. You probably don't need all of these. I don't really know the difference between all of these completely, and it doesn't matter that much. We'll just use the basic web and the Windows x86 probably. Okay, so once you've got that set up, you should have this kind of screen here with web and Windows desktop. Let's do desktop first because it's actually way easier. So you want to click on that, make sure runnable selected. I'm going to set a path, make a new folder called C. In the PC folder, let's see, file Venusian Rescue .exe. Give it a file name. It says it has to be an exe here, so that's good. And that's good. So put it where you want it. I don't think we need anything else here. There's probably tons of special stuff you can do, but whatever. Click on Export Project, save, and it should export for you. It should be really quick. PC, and let's try to run this. If you click on it, and you have a game you can share with your friends. Just share this folder, and it will work just fine. It's 100 megabytes. That's crazy, but I mean, a lot of that is just Godot overhead. If you did a Unity game, it would be way bigger. Now let's figure out how to put a web game up on itch.io. Let's go to web here. And this is a little weirder, and I actually messed it up when I first did it. So you'll see here it says export path. I'm going to, let's see, I'll put it in up a level, builds, and I'll make a new build folder called, what's it called? Web. And it wants to be called VenusianRescue.html. Actually, that's not good. This has to be called index.html. If it's not called index.html, everything will go wrong. So index.html only. Click on Export Project. And you'll see, if you go to your web builds folder, you'll get this. What I want you to do is select everything, right click, click on compress to zip files fine. I'd call it just Venusian Rescue. Now it's deadly important that there's a file called index.html in here. If it's called something else, you will die. It'll be messy. Okay, now you want to go to itch.io. This is my itch.io. I haven't actually uploaded anything here yet. Click on the dropdown, click on upload new project. You can title it. You can give it a cool URL, description. Save your alien buddies from the terrors of Venus in this thrilling snake-like classification. This is a game. It's a HTML game, and it is a prototype because whatever. Pricing, I'm setting it to no payments. If you feel really gutsy, you can make it worth $10,000. I don't think anyone will pay that for it. Upload files, and you want to find your game here, web, and your zip file goes here. If you don't have that index.html file in there, it will break. Say this file will be played in the browser, and that's good. Embed in page, and I think it's 1156 by 640. We can check that for sure by going to our thing here, play 1152 times 648. It says up in the corner here. 648. Frame options, mobile friendly. Don't worry about it. Automatically start on page load. That's good. Full screen. Sure, man. Details. Made with the cool hovering skull tutorial on YouTube. Genre. This is a arcade game, puzzle game. I don't know, man. This is a sports game now. Tags. I don't want to do this right now. There's no AI used in this. And the custom noun itch.io will call this a game unless you tell it it's something else. I'm going to call it immersive interactive experience. Sure, and let's leave it to draft. Save and view page. My noun's too big? Goddamn. Immersive experience. Welcome to your immersive experiences page. That's so dumb. Okay, cool. And that just works. Now you should be able to share this around. It's in draft though, so only you can see it until you set it to published or whatever, which you should be able to figure out. And if I press full screen, dang, that's big. All right, that is how you publish something on itch.io. And you could also upload that PC version 2 as a download. You can figure that one out yourself. But here we go. You've practically released a game here. Wow. All right, that's it. Congratulations, you finished. This was obviously not a complete introduction to Godot. It was kind of a introduction to how code works in Godot. And there's a ton of other things that we have to learn, both in code and out. Things like physics, signals, UI, audio, animations, rotations, 3D, networking, and complex data handling. But you can build up to that. So just keep learning. If there's a lot of interest in this, maybe we will revisit it and do things like add some UI, like a menu, maybe add some sound effects and music, work in signals and events. These are great to learn about. I have a huge video on them somewhere that you can look up. We'll make the code a little more modular by making new classes that we can reuse and that might simplify things a lot. We will maybe introduce something like persistent high scores or something like that that can be saved on your computer, or maybe even eventually on an online leaderboard. Cool. I hope you enjoyed that. Leave a comment if you did, or leave a comment if you didn't. It helps me either way. Okay, goodbye.